Hello there and welcome to the Sleepumentary channel. You look up and though you can't see it with the naked eye, there is a quiet agreement written into the paths of worlds. Mercury skims close to the furnace. Venus drifts in slow brightness. Earth keeps time with the seasons. Mars steps out a little farther and the giants, Jupiter, Saturn, Uranus, Neptune circle in their wide blue dark lanes. All of them move the same way around the sun when viewed from above its north pole, as if obeying a sentence spoken long before they were born. That shared direction is not a coincidence. It is a memory. The solar system remembers how it began, and it remembers through motion. To touch that memory, you drift back in imagination to a time before planets existed, before the sun had a surface to shine, before there was anything here but a cold, dim cloud. 4.5 billion years ago, our neighborhood was a fragment of a much larger molecular cloud, hydrogen and helium in great abundance, laced with a fine dust of heavier elements, made in older stars, carbon, oxygen, silicon, iron. It was not a sphere of serenity. It was irregular, frayed around the edges, stirred by whispers of distant supernova shock waves and the soft tug of the galaxy's spiral arm. In all that unevenness, there was one small imbalance that mattered most. The cloud turned just a little. So before we continue, hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You're the reason we can keep following the impossible, and for that, thank you. Gravity began its patient work encouraging denser patches to become denser still. Where the cloud thickened, radiation could no longer slip out easily, the gas cooled and lost pressure and collapse accelerated. What had been a soft expanse became a slow whirlpool. As it shrank, it spun faster the way a skater draws in their arms and turns more swiftly. This is the conservation of angular momentum, not a law written by human hands, but one discovered in the behavior of everything that rotates. Angular momentum is the universe's way of keeping a promise. If you begin to turn and nothing steals your twist, your turn will endure. When matter gathers, the spin intensifies. When it spreads, the spin relaxes. In this give and take, the cosmos preserves a kind of memory not in images or words, but in the steadiness of a direction. As collapse proceeded, the turning cloud flattened. Collisions between dust grains cancelled their up and down wanderings, and left only the roundabout motion that wastes the least energy. The whole structure settled into a disk thin compared to its width, dense toward the center, where the pressure rose high enough for something new to begin. Hydrogen atoms were pressed together into heat and light. Fusion took hold, the core ignited. In that ignition, the sun was born not all at once, but as a slow, brightening heart inside the disk. Around it, a rain of tiny solids stuck, separated, struck again, and stuck once more. Pebbles grew into boulders, boulders into mountain-sized bodies, and those into planetesimals. The disk was a nursery, its floor swept by endless traffic, its air bright with fine dust. In this churning place, direction was a teacher. Everything learned to move the same way because everything learned from the same spin. Think of angular momentum as inheritance. The sun holds most of the system's mass, but the disk held much of its motion, and the new worlds gathered that motion the way seeds gather the wind that carries them. The orbits they took up were not chosen. They were remembered. Counterclockwise, as we define north and south in our celestial maps, every planet fell into that rhythm because every grain of dust that built them had already been circling that way. And the plane they share, the ecliptic, is the ghost of the old disk's surface, a geometrical keepsake pressed thin across billions of miles. It was not peaceful, not in the way your heartbeat at midnight can be peaceful, but it was ordered inside its chaos. There were collisions that would have rung like bells if space could carry sound mergers that changed the fates of worlds, close passes that tilted spinners, shattered mountains, remade landscapes. Yet through every shock the larger rule held. You can flip a planet's axis with a strike. You can wobble its tilt with a neighbor's tug. You can lengthen a day by exchanging momentum between rock and atmosphere. But to reverse the grand drift of an entire system would demand an intruder of impossible audacity. The direction persisted because the system was together in keeping it. Motion shared is hard to steal. If you could have hovered beside the forming sun safe somehow in the storm, you would have seen the disk veined with spirals, density waves curving like the arms of a slow hurricane. In their crests, material gathered. In their troughs, material thinned. Along these filigreed paths, worlds to be swept cleaner lanes and grew their gravity, plucking pebbles from the wind. The closer a world orbited to the center, the quicker it moved, the farther the slower an old harmony that still plays Mercury racing in 88 days, Neptune strolling in 165 years. The tune's tempo changes with distance, but the melody keeps its key. Even the sun's own body records the remembered spin. It turns differentially faster at the equator than at the pole's threads of magnetism, winding and unwinding on 11-year cycles that breathe through the corona and out into the solar wind. That wind is not random. It spirals outward with the same handedness as the disk that birthed it, a vast invisible imprint of the original twist, inscribed in charged particles. It is an echo still travelling. You might wonder why counterclockwise. The truth is that counterclockwise is a label we made anchored to how Earth defines north, tied to how our maps are drawn. Had we defined the other pole as up, we would have said clockwise. What matters is not the word, but the continuity. There is a chosen axis chosen by the accident of initial conditions, and around that axis motion is loyal. Half of all star systems may spin the opposite way. Ours spins the way it does, because that is how the cloud turned when gravity first leaned in. It is tempting to imagine that order like this demands intention, that symmetry and alignment must be the marks of a careful designer. But no external hand is needed for disks to flatten and orbits to agree. The universe prefers arrangements that waste the least energy paths that can last. Collisions drain away the useless motions. Gravity balances what remains. What we call order is what survives, and what survives carries a history that can be read if you know what to listen for. Here the language is rotation. The alphabet is the preserved direction of a spin nobody witnessed, only deduced from the way everything still moves. So tonight, as you picture the planets slipping like beads along their circular threads, you can think of them as dancers, keeping time with a drum. No one hears anymore, except in the way their feet remember to step. The drum is the old cloud's turn, the beat is angular momentum, and the choreography is inheritance. This is the echo of beginning a small imbalance amplified by collapse, a faint whirl made firm by gravity, a shared direction that turned dust into worlds and kept them from losing one another. The story will deepen. The system is flat but not perfectly, aligned but rumpled, calm but weathered by ancient storms. Imperfections remain, and those imperfections also speak. Yet before the wrinkles and the exceptions, there is this simple, generous law motion once given remains. The planets do not merely orbit, they remember, and in their steady counterclockwise murmur you can hear the first agreement the solar system ever made with itself, still honoured after billions of years. There is a law in the universe so simple, so quietly absolute, that it governs everything from the spin of a galaxy to the twirl of a child on ice. It says that when something turns, it keeps turning unless something stronger stops it. The name scientists give it is the conservation of angular momentum, but it could just as well be called the dance that never stops. Imagine a figure skater in a vast, silent rink. Arms outstretched, she spins slowly. Then she draws her arms in, folding closer to herself, and instantly her speed increases. She has not added energy, she has only changed her shape. The same amount of rotational momentum must now move through a smaller space, so the motion quickens. The universe works in exactly that way. When clouds of gas collapse, when stars are born, when galaxies gather from dust, they pull their arms in and they whirl faster. Creation at its core is a slow contraction that turns into a spin. Billions of years ago, before the first sunrise ever fell on the young Earth, a massive molecular cloud floated in one of the Milky Way's spiral arms. It was ancient starlight made cold hydrogen and helium, mostly with fine traces of heavier atoms, the ashes of earlier generations of suns that had lived and died. That cloud stretched across hundreds of astronomical units, enormous, and still like smoke suspended in the dark, yet still is an illusion. Nothing in the cosmos is perfectly motionless. Even the faintest swirl is enough. Somewhere within that cloud turbulence created a tiny rotation barely perceptible, but it was there. And in a universe that remembers every spin, that was all it needed. Gravity began its patient invitation inward. The denser parts of the cloud grew denser still. The temperature rose as particles crowded together. As the cloud contracted its rotation, intensified an invisible pirouette in the void. Angular momentum could not vanish, so the slower turn of the vast cloud transformed into a faster spin as it shrank. You could have called it cosmic ballet matter, moving toward its own center, speeding up the tighter it was drawn. If you could have watched the process from light years away, time sped up 1,000-fold. You would have seen a gentle drift of mist gather into a luminous whirlpool. The swirl became a disk, a flattened sheet of gas and dust circling a bright newborn star. The sun was taking shape at the center, igniting as hydrogen fused into helium. Gravity's potential energy turned into radiance. It wasn't sudden, not an explosion, but a rising breath, a core that began to glow, because the inward pull of gravity had nowhere left to go but into heat and light. In that transformation, the universe remembered its oldest rule. The slow turn of a cloud became the steady spin of a star and the circular orbits of planets to be. It was the same dance repeated at a new scale. Every atom, every spark of dust carried part of the original movement. What we now call the ecliptic plane was simply the shape that balance took the geometry of motion, learning to conserve itself. Across the universe, telescopes have caught other newborn stars frozen in that same moment of creation. The Alma Array in Chile has photographed young suns wrapped in glowing disks of dust, HL Tauri Beta Pictoris, T Isla Bu Hydro, each one an echo of our own beginning. They all show the same flattened spin, the same inward brightening pattern. It is not unique to us. It is the signature of gravity's music playing everywhere. Even now, the James Webb Space Telescope peers into distant nurseries, seeing infant systems wrapped in foggy spirals, cosmic dancers rehearsing their first turns. The physics that choreographs them is indifferent yet elegant. Angular momentum is not a force, it's a conservation and memory the universe refuses to erase. When a star collapses into a neutron star after a supernova, its rotation can increase from once every few weeks to hundreds of times per second. When a galaxy forms its sprawling arms, curved from the same hidden spin, the same equation binds them. What turns keeps turning, and what shrinks spins faster. This principle links the skate of the star and the spiral galaxy in one seamless act of continuity. Our sun obeys it still. At its equator, it rotates roughly every 25 Earth days. Near the poles, every 35. It is not a solid body, but a sea of plasma, and even its magnetic fields twist with that inherited motion. The solar wind flowing outwards spirals into space in a vast helix, the Parker spiral, its pattern carried through billions of kilometers. That twist is the sun's fingerprint, the same spin scaled outward into the emptiness, sculpting the magnetic weather that touches Earth's auroras and reaches all the way past Pluto. When you stand beneath the night sky, you are standing inside this slow, unstoppable spin. Every atom in your body was once part of that same nebula cloud. The calcium in your bones, the iron in your blood, all once swirled in a gravitational dance around a forming star. You're built from dust that learned to move in circles. You don't feel the motion, but it's their Earth, turning eastward at over 1,000 kilometers an hour, orbiting the sun at nearly 30 kilometers per second, the sun itself drifting around the Milky Way's center at 220 kilometers per second. The dance never stopped. It only changed partners. It's worth pausing to feel what that means. The universe doesn't just spin it, remembers that it knows how. From the very first rotation of hydrogen clouds to the swirl of galaxies billions of light years away, every act of creation begins by keeping what it already has in motion. In a cosmos where most things fade, motion endures. It's the only memory written into the structure of everything. Every planet orbiting today, every moon and asteroid is following steps choreographed long before Earth existed. When you look up, you're not watching movement in the present. You're seeing the continuation of an ancient performance that began in silence and has never once broken rhythm. And if there is poetry in physics, it is here in the law that turns collapse into grace. Gravity pulls inward, angular momentum turns sideways, and the result is neither fall nor rest, but dance. The universe never stands still. It contracts and spins, always conserving a trace of its first motion, as though creation itself cannot forget the joy of turning. The cloud does not begin as a disk. It begins as weather eddies of cold gas, ripples of pressure, filaments collapsing into knots and then unspooling into filaments again. In the half-light of a molecular cloud, Turbulence is the first language uneven three-dimensional, full of updrafts and crosswinds. Hydrogen flows past hydrogen. Dust grains drift like ash in a breath that never quite settles. Nothing here is flat. And yet within this disorder, rotation quietly accumulates. Every small whirl that leans the same way adds to a larger lean, and gravity patient as always makes a promise. What falls inward will remember how it turned. As the cloud contracts, collisions begin to matter. Dust grains bump and kiss and stick. Gas molecules share heat and slow one another's wayward motion. Vertical movements, those that vault above and below the center, lose energy fastest because every crossing of the nascent midplane is a chance to collide and be softened. What lasts is the sideways motion, the circular threading around the center of mass, because it spends the least. In this sense, the forming system is thrifty. It sheds the expensive up and down and keeps the affordable around and around. Over time, the three-dimensional weather subsides into a two-dimensional wind, a rotating sheet of gas and dust, thin compared to its width, luminous at the heart. We have seen this with our own instruments, the Atacama Large Millimeter Submillimeter Array. ALMA has photographed young stars whose disks look like records pressed in starlight. H. Altari still, a cosmic infant, appears banded with rings and gaps as if invisible planets already swept lanes clean. T-UP-W Hydri shows the same concentric grammar. Beta Pictoris older offers a debris disk that from our angle lies nearly edge-on, a ruler-straight beam cut across the dark. The James Webb Space Telescope adds infrared nuance to these images, warm dust traced by Miri complex organics, and ice is sketched by NIRSPEC, the faint texture of spirals and shadows that hint at forming worlds. In system after system, the wild fluff of a cloud becomes a disciplined plane. The pattern is not special to us. It is the habit of matter when gravity and rotation have time to speak. How does thickness yield to thinness? Part of the answer is collisions. Another part is viscosity, though not the clinging thickness of honey in a spoon, but an effective viscosity born from turbulence itself. Gas in a disk does not turn like a rigid wheel. Inner layers orbit faster than outer ones, and that shear the speed difference with radius tangles and stretches small eddies into long filaments. In the classic A-disk picture, we summarize this complex exchange with a single letter AR, says how efficiently turbulence transports angular momentum outward, allowing mass to drift inward. Inward flow feeds the young star, outward transport spreads the disk. Together they flatten and organize, but turbulence is not merely a mess, it is a machine. In the weakly ionized gas of a protoplanetary disk, even a faint magnetic field can couple to the flow. Where ionization is enough starlight near the surface cosmic rays that slip in heat near the center, the magneto-rotational instability MRI wakes. MRI is a beautiful paradox. It takes a stable shear faster inside, slower outside, plus a magnetic tether, and turns them into a self-sustaining tap of angular momentum from inner to outer regions. Imagine two neighboring rings of gas tied by elastic magnetic threads. The inner ring orbits faster and pulls ahead. The thread stretches. Magnetic tension drags the inner ring back and tugs the outer ring forward. The inner ring loses angular momentum and sinks. The outer ring gains and drifts outward. The stretch continues. Turbulence blossoms, transport accelerates. From a nearly invisible magnetic whisper, a powerful viscosity emerges. The result is not only radial spreading, but vertical calming MRI stirred layers exchange momentum until the midplane becomes the place where vertical motions are most diminished and solids most likely to settle. Not all radii and heights are equally alive. In the midplane, far from ionizing, light charge carriers can be scarce. There, MRI can fall silent, creating dead zones of low turbulence sandwiched between more active surface layers. Even in the quiet, other instabilities stir. Vertical shear, the subtle change in orbital speed with height, can drive gentle overturning. Dust gathering into a midplane traffic jam can trigger the streaming instability particles drag on gas. Gas drags back and clumps grow dense enough to collapse under their own gravity. What looks like placid thinness from above is up close layered weather-active skin, quiescent heart pockets of mischief where planets take their first breath. As the gas calms, vertically solids settle like snow. The smallest grains feel gas drag most strongly and drift inward slowly. Larger pebbles settle faster toward the mid-plane, creating a dense sheet, only a few % of the disk's height. In that sheet, relative speeds are low enough for sticking to win. Frost lines where water carbon dioxide or carbon monoxide can freeze act like chemical switchbacks, increasing the stickiness and abundance of solids beyond each line. At these icy frontiers, pebbles grow efficiently. Pebbles glue into boulders. Boulders concentrate until gravity pinches them into planetesimals in a geological instant. Gaps open where young giants stir the gas. Spirals unfurl where their wakes curl the flow. The thinness is no longer only geometry. It becomes a scaffold for architecture. Alma's crisp rings and JWST's heat sketch spirals are the photographs in the family album of this process. In H.L. Towery's bright bands, we read the places where dust is pooled and where new worlds likely feed. In Beta Pictoris's razor line, we see the long-lived debris of collisions among the children of the original disk grains, ground from planetesimals shepherded by unseen planets into warps and clumps. Even the shadows, dark wedges cast by a slightly tilted inner disk across a brighter outer one, tell us the disk is not a single slab but a stack of planes coaxed into near alignment over time by the same collisional damping that thins it. All of this viscosity born of turbulence, born of shear and magnetism settling, born of collisions, growth born of drift, conspires toward a single outcome, a rotating sheet that wastes as little vertical motion as it can. Gravity pulls inward, pressure cushions outward, rotation diverts the fall into orbit. The equilibrium is not static, but sustained gas trickles starward. Angular momentum leaks rimward. The disk thins as it lives, then dissipates as the new stars light, and wind erode it from the top down. What remains are leftovers, asteroids, comets, and the finished worlds clearing their lanes. There is a tenderness in the efficiency. The universe does not flatten because it loves circles. It flattens because circles are what survive. In a medium where everything bumps everything else, the only motions that last are those that do not invite collisions. Motions parallel to the plane around the center, in step with neighbors. Vertical noise cancels itself. Lateral harmony accumulates. You can think of the protoplanetary disk as a choir, finding its pitch at first a jumble of voices, then through listening and adjustment a shared note that each singer can hold. And yet even choirs have texture. Slight misalignments remain. Warps persist at the edges. Inner and outer disks can differ in tilt if a forming planet or a passing star once pressed a knuckle into the clay. The thinness is impressive on the scale of the solar system, flatter than paper, but it is not perfectly flat. Those small deviations matter. They carry the memory of the disk as weather long after the gas is gone. Soon we'll ask why so much of the solar system hugs a single invisible sheet, why nearly every major world orbits within a few degrees of the same plane, as if obeying a rule that prefers 2 dimensions over 3. The answer will be mechanical, not mystical. But before we follow the planets into that thin geometry, it helps to remember the path they took from turbulence to sheet, from 3-dimensional weather to a near 2-dimensional wind guided by gravity, tamed by collisions and quickened by magnetism, into a disk where motion could last. The mystery ahead is not that the system is flat. It's how such flatness can be this resilient. If you could hold the solar system in your hands, an impossible model of gas and stone time and light, you'd find it thin, almost impossibly so. The planets all circle within a sheet so narrow that if you scaled the entire orbit of Neptune down to the size of a dinner plate, the height of that plate, the system's thickness would be thinner than a single sheet of paper. Out of the chaos of a collapsing cloud, the universe somehow sculpted near perfection, a flat spinning disk where 8 planets glide as though laid upon invisible glass. But why did everything flatten? Why did a cloud, once shapeless and deep, collapse into a structure that is barely 2-dimensional? The answer lies in the quiet arithmetic of collisions. In the beginning, before the sun was even fully awake, the gas and dust around it moved in all directions, up, down sideways like snow swirling in a storm. Each particle carried its own random path, its own tiny fragment of freedom. But in a dense swarm, freedom has a price collision. Every time 2 grains met, a little of their random motion was lost as heat. Upward and downward trajectories were especially costly because they made crossings through the crowded midplane where most particles congregated. Those grains were constantly bumping into neighbors, bleeding away their vertical energy, settling closer to the plane where motion was smoother, safer, more efficient. Slowly, a kind of calm formed in the middle, a dense rotating belt, thin, As a thought compared to its breadth, the universe left to itself had discovered the geometry of balance. Scientists call this process collisional damping, a term that sounds mechanical, but it is as graceful as erosion. Billions upon billions of micro-impacts did what no single force could. They cancelled chaos. In every strike, the small deviations that pointed up or down cancelled out. What remained was the sideways rotation, the movement that could continue without interference. Carl Sagan once said, "The solar system is a flat disk because collisions made it so." That single sentence captures the beauty of inevitability. The universe didn't plan the shape. The shape emerged from the exhaustion of unnecessary motion. You can picture it with something familiar. Spin a spoonful of honey on a plate. At first, it swirls unevenly, clumps lifting and falling edges thicker than the center. But as it spins, the viscous drag smooths the surface. The honey spreads into a thin disk, every ripple subdued into the same circular flow. Or think of a potter at her wheel. The lump of clay begins crooked, leaning too high on one side. As the wheel turns, her hands press gently against it, feeling for irregularities. The excess is drawn out, the bump smoothed the form, lowered and widened until it becomes a vessel, balanced between gravity and motion. That is what happened to the solar nebula collisions as the potter's hands gravity as the wheels spin, shaping chaos into a symmetrical form that could hold worlds. What's remarkable is how fast this flattening occurred. Simulations suggest that within just a few 100,000 years, a blink in cosmic time, the majority of the gas and dust had settled into a thin, rotating layer. The thickness of that layer relative to its diameter was smaller than 1%, and once it reached that equilibrium, the geometry became self-sustaining. Gravitational attraction toward the mid-plane held particles in the sheet, while the angular momentum of rotation prevented collapse. Like the tension in a taut drum, these opposing pulls locked the structure into stability. Evidence of that ancient flattening is still visible every night if you know where to look. On exceptionally dark mornings just before sunrise or just after sunset, a faint triangle of light sometimes glows above the horizon. It looks like the ghost of a dawn that hasn't yet arrived. That is the zodiacal light sunlight scattering off tiny dust grains that still orbit within the same flattened plane as the planets. The solar system's disk, once opaque and fiery, has thinned into this faint silver mist. Every mote of that dust is a relic of collisional damping, a survivor of the process that made order possible. Even the paths of the major planets confirm it. Mercury, closest to the Sun, orbits only 7 degrees above the plane. Mars leans by less than 2. Earth's own orbit deviates so little that its plane defines the measure, the ecliptic, by which all others are compared. The Moon follows almost the same line, tilted by just 5 degrees. These small angles are not imperfections, but fingerprints of how energy was spent. Collisions could never erase every wobble. They could only erase most of them. What was left, those few degrees of tilt, are the wrinkles of an otherwise ironed sheet. There's a humility to this outcome. The solar system's order is not the result of a single grand mechanism, but of countless small events that cancelled one another out. Every impact that robbed a particle of vertical speed was a vote for calm. Every merger that reduced turbulence was a decision toward simplicity. And once the system found its plane, it stayed there. Because in physics, the most stable shape is always the one that wastes the least motion. This flatness explains more than geometry. It defines visibility itself. When you trace the path of the sun, moon, and planets across the sky, you are following the ecliptic, the thin band where that ancient disk once spun. Astrology's zodiac owes its name to this alignment. So do the gentle lanes of the Milky Way seen edge on through our galactic disk. The reason every bright wanderer in the night sky appears along roughly the same path is not coincidence, it's heritage. Every world we can see with the naked eye lives on the same cosmic platter, the remnant of those billions of damped collisions. Flatness also sets the stage for stability. In a nearly two-dimensional system, gravitational interactions are predictable. Planets pass each other on near-parallel tracks, avoiding catastrophic encounters. Their inclinations remain small, their orbits evolve slowly. If the solar system were a chaotic three-dimensional cloud of trajectories, planets would constantly cross paths, their gravities tugging each other into new directions, leading eventually to collision or ejection. Flatness is not only elegant, it's protective. Still, there is poetry in the imperfections that remain. Mercury's 7 degree tilt, Pluto's 17 degree. The slight warps in Saturn's rings, they are reminders that no smoothing process is complete. Each deviation is a fossil of an ancient jolt, a passing body, a gravitational resonance, a relic of motion that refused to die completely. The same collisions that made the system flat could not erase memory entirely. In the geometry of the orbits, the past is preserved as angles. You might imagine the forming solar system as a kind of cosmic centrifuge. The sun at its center was the pivot. Everything else was sediment in suspension. As the system spun, centrifugal force pulled the heavier materials outward, while gravity drew everything inward. Between those two great arms of force, a flat equilibrium formed a dance of push and pull, expansion and compression. Even now, the sun's gravitational grip keeps every planet near that ancient plane, while angular momentum keeps them from falling into it. The system is still turning on the same wheel, and if you could tilt your head high enough above the north pole of the sun, looking down across the orbits of the planets, you'd see something that looks surprisingly human, a record spinning. Each groove an orbit, each track a note in an ongoing symphony of motion. Everything we are Earth's day, its seasons, its climate, depends on that disk staying true to its original form. A universe that once roared with random motion learned to find its balance through impact and loss. The solar system is not flat because it was born simple, but because it was born chaotic and grew tired of fighting itself. It spun, collided, settled and smoothed until only the most economical movements remained. What we see now is the geometry of patience. Yet perfection is an illusion. Even in this flatness, there are small tilts and warp secrets that tell us the system's symmetry was hard-won and never absolute. In the next step of our journey, we'll look closer at those wrinkles, the inclinations, the slight misalignments and the hidden forces that disturb the calm sheet of orbits. The solar system may appear like a flawless platter of light, but its true story lies in the tiny bends, the subtle asymmetries that survived creation's smoothing hands. From a distance, the solar system looks serene, planets gliding in perfect circles, each one knowing its place, as though some invisible geometry holds everything still. But look closer, and you realize that this calm isn't the absence of motion, it's motion perfected. Flatness in this context is not merely a shape, it's an equilibrium, a balance so complete that the universe itself seems to take a breath and hold it. Every force has found its counterpoint. Gravity pulls the planets inward, their orbital motion pulls them outward. The two never win against each other, they only agree to trade energy in an endless negotiation. The result is stability, not the kind that resists change, but the kind that absorbs it. The thin plane of the solar system is that compromise made visible a geometry of calm carved from the chaos of falling matter. When astronomers speak of the ecliptic, they mean this very balance, the invisible tabletop of space where nearly every planet moves. It's the plane of the ancient disk now frozen into orbits so smooth that even the moon and most asteroids follow within a few degrees of it. For billions of years, the ecliptic has been the gravitational neutral zone, the surface on which planetary gravity, solar pull and the relic spin of the nebula cancel into long-term peace. Flatness equals stability for a simple reason: when orbits share the same plane, their gravitational tugs act mostly sideways, not up and down. Sideways tugs distort paths, but rarely destabilize them. Vertical ones, however, can throw a world completely off its track. By aligning in a common sheet, the planets minimize those disruptive forces. It's the same principle that makes a school of fish move more efficiently when they swim parallel, or a murmuration of starlings flow as one body, each individual motion amplifying coherence instead of chaos. In cosmic terms, this harmony wasn't designed, it evolved. Collisions erased the noisy vertical energy until the only surviving pattern was the one that conserved the most motion with the least conflict. The solar system didn't seek perfection, it simply discovered the path of least resistance, and that path happened to be flat. When the James Webb Space Telescope captured its first deep infrared images of Beta Pictoris, a star about 63 light-years away, it showed a reflection of our own story. The star is only 20 million years old and adolescent by cosmic standards, and yet already encircled by a razor-thin disk of dust and debris. In Webb's view, the disk glows like a halo of gold seen edge on nearly as straight as a laser. Embedded within it are signs of planetary construction arcs, clumps, ripples. The structure is so geometrically precise that it could be mistaken for an architect's drawing, except that no architect designed it. Gravity and time did. That image is more than a photograph, it's a mirror held up to our past. It tells us that calm is not a gift from the beginning. It's an outcome of turbulence that has learned to restrain itself. Every thin ring of beta pictoris, every symmetrical layer is a relic of violent beginnings subdued into grace. Chaos did not vanish. It matured. The same equilibrium rules our neighborhood. Picture Earth's orbit as a stretched ribbon of light around the sun. Jupiter's path, immense and slow, runs almost parallel to it. Mars's orbit only leans by a single degree and a half. From afar, these ribbons overlap, forming the delicate weave that keeps the system from unraveling. The geometry is so precise that if you were to model all 8 major planets to scale, you could slide a single sheet of paper between their planes of motion and barely feel the difference. Yet this precision was never meant to be permanent. It's a dynamic, calm, alive, breathing and subtly flexing. The orbits of the planets oscillate over time. Tiny gravitational pulls accumulate shifting eccentricities and inclinations like slow heartbeats. Over tens of thousands of years, Earth's tilt wobbles, altering the timing of ice ages. Over millions, even the orientation of the ecliptic drifts as Jupiter and Saturn tug it like tides. Stability does not mean stillness. It means coherence across change. Astronomers have a word for the shape of this balance, the Laplace plane, the mathematical average of all orbital motions, the equilibrium where every force finds a shared reference. It's a dynamic plane gently adjusting to the collective rhythm of the planets. Each orbit contributes a small voice to its position, and together they maintain the harmony of the solar symphony. The sun conducts through gravity, the planets play their notes in resonance, and the resulting composition is almost but never perfectly in tune. Flatness gives the system predictability. From it flow the cycles that make time familiar, the seasons, the phases of the moon, the periodic returns of comets. Without a stable ecliptic, the heavens would be erratic. Days and nights would stretch and shrink without pattern. Seasons would come at random. Our sense of order of years repeating and dawns returning is born from that nearly perfect alignment. The geometry of calm is also the geometry of habit of repetition, so consistent it feels like peace. But nature never leaves perfection untested. Even in the flattest system, small inclinations creep in. The gravitational embrace between planets, never perfectly symmetric, induces subtle tilts. Mercury's path rises 7 degrees above the ecliptic. Pluto's arcs 17 below and above in a looping inclination that takes centuries to complete. Each of these deviations is a reminder that stability is not a straight line. It's a balance beam walked by giants. They wobble, but they do not fall. If the solar system were drawn to scale in light, you'd see it as a glowing disk with tiny ripples. These ripples are history echoes of collisions and near misses that left their signatures as inclinations. They're also a promise that the system is alive, not frozen. The tiny tilts of orbits are the scars of its youth preserved in geometry. Perfect order would have meant fragility. A system so stiff it could never bend would shatter at the first disturbance. The small imperfections, those gentle inclinations, are what make longevity possible. Flexibility is endurance written in angle. You can feel it poetically too. The calm of the solar system is not the calm of silence. It's the calm of rhythm. Each orbit is a drumbeat that doesn't drown the others. Every planet's gravity is a note that bends space without breaking the chord. Together they form what physicists call gravitational equilibrium and what poets might call grace under tension. And when you see that faint band of zodiacal light before dawn, the soft triangular glow rising from the horizon, you're looking right along the ecliptic, peering through the plane of balance itself. The dust that scatters that light still orbits in the same sheet that once held the forming planets. You're seeing the solar system from inside its own geometry of calm, the living proof that chaos can learn restraint. Yet even serenity has edges. Beyond this near-perfect sheet of motion lies evidence of small rebellions, tiny upward and downward tilts that survived the smoothing. The next part of this story belongs to those imperfections, the gentle warps and inclinations that remind us that calm is never absolute, and that even in the most ordered systems, the universe always leaves room for a little disorder to breathe. The solar system from afar appears flawless, a clockwork of concentric circles turning in unison around the sun. But even the most perfect disks wrinkle when time presses against them. Look closer and you'll see the gentle folds, the inclinations, the small tilts of each planet's orbit that break the illusion of perfect flatness. The geometry of calm, it turns out, still carries the fingerprints of its turbulent past. Mercury, the swiftest of all, skims the Sun with a path tilted 7 degrees above the ecliptic. Venus leans only 3. Earth, our reference point, defines the plane itself. Mars rises and falls by less than 2 degrees, an obedient dancer slightly out of step. Farther out, Jupiter and Saturn waver by just a single degree, restrained by their immense gravity. But then the sheet begins to ripple. Uranus tilts a little more, Neptune a touch beyond that, and at the edge the pattern breaks entirely. Pluto, once called the 9th planet, swings, in a long thin ellipse tilted 17 degrees off the common plane, looping above and below the ecliptic like a forgotten stitch in an otherwise seamless fabric. If you could stretch the solar system into a colossal golden disk and run your fingers across it, you'd feel these differences as tiny ridges imperceptible from a distance, but real under the touch. The disk is not a polished mirror. It is a memory etched in motion, a cosmic sheet forever creased by its own history. These wrinkles are not flaws, they are fossils. Each tilt, each deviation tells a story about what the early solar system endured. In the beginning, when the planets were still assembling from planetesimals, the space between them was crowded full of half-formed worlds, rocky embryos and icy wanderers caught between gravitational fields. Collisions were common, and collisions never occur in perfect alignment. Every impact added a small twist, a change in orbital inclination, a vertical scar on an otherwise flat design. One planet might be struck by a late-arriving body from above the plane nudging its path upward, another by a glancing blow from below shifting it downward. The grand disk survived, but its surface was forever rumpled. Even after the age of impacts waned, another sculptor took over gravitational resonance. No 2 planets orbit in complete isolation. Each tug from a neighbor, repeated again and again at regular intervals, can accumulate like a rhythm that shakes the floorboards of a house. When 2 planets' orbital periods align in simple ratios, say 2 or 3 turns, of one for every one of the other, their pulls reinforce each other. Over millions of years, this resonance can tilt or stretch their paths, sometimes dramatically. That's what happened in the outer solar system. Long after their birth, Jupiter and Saturn began to migrate, sliding outward and inward through the leftover disk of debris. Their gravitational duet acted like a tuning fork, sending resonant vibrations through the region beyond Neptune. Smaller worlds, the proto-Plutos and frozen remnants of planet formation, were caught in those oscillations. Some were ejected, completely sent tumbling into interstellar darkness. Others found stability in eccentric tilted orbits locked in resonance with Neptune. Pluto itself is the most famous survivor, trapped in a 3-2 resonance, completing 2 orbits for every 3 of Neptune's. The resonance protects it from collision, even though its path crosses Neptune's orbit in projection. Their rhythms never let them meet, but that same resonance tilted Pluto's orbit over time, lifting it 17 degrees above the plane, like a thread pulled too tight. The result is a solar system that is orderly but not uniform, disciplined yet scarred. Each world carries the mark of where it collided, where it was tugged, where it remembered. The inclinations are not random. They are signatures of ancient negotiation between chaos and harmony. Mercury's 7 degrees may trace back to the gravitational influence of Venus, its near neighbor. Their orbits interact in subtle resonances that slowly shift Mercury's inclination and eccentricity. Venus's own mild tilt may be the softened aftermath of countless small impacts and the tidal drag of the Sun. Mars's 2 degrees, barely enough to notice, may be the residue of the late heavy bombardment when asteroids and comets rained upon it, tilting its orbit by fractions that compounded over eons. Further out, Uranus and Neptune likely experienced a different kind of disturbance, planetary migration on a grand scale. In the Nice model of solar system evolution, the giant planets did not form exactly where we find them now. Instead, they shuffled positions after the birth of the Sun, scattering planetesimals like seeds and exchanging angular momentum. Each small gravitational kick tilted their orbits slightly. These changes, too small to erase the system's overall flatness, were enough to give it texture. The smooth honey of the early disk gained faint ripples, the permanent creases of rearrangement. You can think of these inclinations as wrinkles in space-time fabric, but also as wrinkles in time itself. For every tilt, there was an event, a collision that happened, a resonance that persisted, a migration that unfolded. The solar system's flatness may define its geometry, but its inclinations define its story. The fact that each planet leans a little differently is what allows us to reconstruct that lost era of violence and adjustment. It's as if the universe once folded the disk upon itself, pressed hard, and when it reopened, the creases remained. Even today, those inclinations continue to change very slowly like tides of geometry. Planets tug on one another, exchanging small amounts of angular momentum. Over millions of years, Earth's inclination oscillates by fractions of a degree. Mars's shifts a little more, contributing to its climate cycles. These are whispers of gravity across time, reminders that stability is always dynamic. When astronomers model these motions, they find that the system behaves almost like a breathing organism. The inclinations rise and fall in gentle cycles, gravitational sighs that take tens of thousands or even millions of years to complete. The sheet bends and straightens but never tears. Each motion cancels another somewhere else, preserving the grand balance that keeps the solar system intact. And so from above, what looks like a perfect platter is in truth a living surface, one that flexes, trembles, and remembers. The inclinations are its wrinkles, the record of its youth pressed into its very orbit. The solar system's calm isn't the calm of stillness. It's the calm of something that has survived movement, learned its rhythm, and chosen to continue spinning with grace, despite its scars. In the next breath of this cosmic story, we'll meet the great sculptors who gave those wrinkles shape the giant planets themselves, Jupiter and Saturn, whose immense gravity played the role of both hammer and tuning fork. They are the keepers of the rhythm that set every smaller world in motion, the reason the sheet is creased but not torn, stable, but alive. The geometry of calm may be the rule, but its texture, its character, its depth come from the gravity of giants. From the edge of the night sky, two immense bodies watch over the rest, Jupiter and Saturn, the Titans whose invisible gravity defines the rhythm of everything else. The smaller worlds, Earth, Mars, even distant Pluto, may seem to follow their own paths, but in truth, they dance to the baseline these two giants play. If the Sun is the conductor of the solar symphony, Jupiter and Saturn are its drums, deep, resonant, unrelenting. Every orbit in the system, every inclination and eccentricity carries their imprint. When the solar system was young, the giants were the first to reach full mass. Their formation changed everything. Jupiter, more than twice as massive as all the other planets, combined became the gravitational sculpture of the entire neighborhood. Saturn, only slightly smaller, joined as a counterpoint. Together they generated a web of resonances that swept through the solar disk like invisible tides. A resonance, in the simplest sense, is a repeating gravitational rhythm. When two planets' orbits align in regular intervals, their tugs accumulate. One push does little. A million gentle pushes perfectly timed can move mountains or tilt worlds. In the outer solar system, the Jupiter-Saturn 5-2 resonance. Jupiter completes 5 orbits for every 2 of Saturn's became the great metronome of planetary evolution. Their combined pull rippled inward, disturbing the smaller planets and the asteroid belt while also reaching outward to shape the Kuiper belt's architecture. The resonance works slowly but relentlessly. Over millions of years, it changes orbital shapes, inclinations, and even the long-term stability of other worlds. The flat solar disk we see today is not static. It quivers gently under the rhythm of the giants. Jupiter's gravity alone would have been enough to stir the system, but together Jupiter and Saturn create secular resonances, subtle, long-term gravitational effects that cause planetary inclinations and eccentricities to oscillate like pendulums. These cycles don't break the system, they animate it. Every planet has its own oscillation period and internal breathing of orbit, caused by the push and pull of its neighbours. Earth's inclination, for example, slowly wobbles by about 2 degrees over 70,000 years. Its orbital shape, how circular or stretched it is, changes in roughly 100,000-year cycles. Even the direction Earth's axis points traces a slow circle through the heavens every 26,000 years. These overlapping rhythms are not random, they are the combined echo of the giant's gravity transmitted across space and time. We live inside these oscillations. On Earth, they shape the rhythm of climate itself. In the early 20th century, a Serbian mathematician named Milutin Milankovic studied how these subtle, orbital variations, now called the Milankovic cycles, control the pattern of ice ages. When Earth's orbit becomes more elongated, we spend slightly longer farther from the Sun. When the tilt of our axis decreases, sunlight spreads more evenly across latitudes, softening the seasons. When precession, our slow axial wobble changes the timing of summer. Relative to our distance from the Sun, global climates respond. The frozen rhythms of the Pleistocene, the advance and retreat of glaciers, the rise and fall of sea levels, are not coincidences of terrestrial weather. They are the planetary fingerprints of Jupiter and Saturn written across Earth's climate. Every glacier, every interglacial bloom is a note in the deep music of gravity. Even now, high-precision orbital models show that these giants continue to dictate the tempo of our planet's long-term stability. Remove Jupiter from the simulation, and Earth's orbit becomes chaotic within a few million years. Tilt Saturn slightly, and Mars's eccentricity grows so wild that it might one day cross Earth's path. We survive because the giant's rhythm, though restless, is predictable. Modern simulations give us a clearer view of just how intertwined these forces are. At the Max Planck Institute for Solar System Research, scientists run supercomputer models that follow planetary motions over spans of hundreds of millions of years. They integrate not only gravity, but the subtle feedback of relativistic effects, tidal damping, and mutual resonances. The result is astonishing. The solar system behaves like a network of linked pendulums, each planet's oscillations slightly out of phase with the others yet collectively stable. It's a delicate chaos, not perfect order, but perpetual balance. Meanwhile, the European Space Agency's Gaia mission, which measures the positions and motions of over 1 billion stars, provides an even grander context. Gaia's data allow scientists to trace how passing stars, interstellar clouds, and the Sun's own orbit through the Milky Way may slightly disturb the giant's orbits over eons. These distant influences add tiny beats to the existing rhythm nudges that can shift the timing of resonances by a few thousand years, or tilt the solar plane by fractions of a degree. Simulations using Gaia's data suggest that even subtle galactic tides may have influenced how Jupiter and Saturn migrated after birth, and how their movements rearranged the smaller planets. In this sense, the geometry of the solar system is not purely solar, it's galactic in origin. Our stability depends not just on the Sun, but on its neighborhood. In the language of physics, all these oscillations, secular, resonant, galactic, are just exchanges of angular momentum energy, shifting hands without loss. But in the language of awe, they are the deep heartbeat of the system, a metronome ticking beneath the surface of apparent calm. The giants do not merely orbit, they govern. You can imagine their gravity as the slow bending of an enormous sheet. The Sun sits at the center, and the fabric dips beneath each planet's weight. Jupiter's depression is wide and deep, Saturn's shallower but harmonize beside it. As they circle, their overlapping waves ripple outward and inward, lifting and lowering the smaller bodies. Over time, those ripples settle into recurring patterns, the inclinations, eccentricities, and precessions that define our orbital history. It's a sea of invisible tides, and every world, even our own, floats upon it. When you step outside on a cold, clear night, you're standing on a world that literally breathes in time with Jupiter and Saturn. The shifting angles of sunlight that sculpt our ice ages, the gentle tug that makes our orbit lean or straighten, even the resonance that protects Earth from drifting into chaos, all trace back to those two distant giants moving through their slow, gravitational duet. Their partnership is both stabilizer and artist. They paint the wrinkles in the solar plane, then hold them steady for billions of years. And so, the serenity of the ecliptic, the grand flatness that feels eternal, is really a dance of oscillations so vast, so gradual, that we perceive them as stillness. In reality, the geometry of calm breathes, and Jupiter and Saturn are its lungs. But even they are not alone. Beyond them lies the outer darkness, where the Sun's authority weakens and the system begins to fray, where orbits tilt more boldly, resonances twist into new shapes, and the sheet of order ripples toward its edge. That's where we turn next to the rhythm of the solar system's heartbeat, extended across millions of years, the slow inhalations and exhalations of a cosmos that never truly rests. If you could speed up time, turn the sky into a quiet blur, and let 1 million years pass between breaths, you would see the solar system move in a way no single night can reveal. The orbits themselves would seem to sway, their ellipses would rotate like slow gears, their orbital planes would tilt and untilt in long cycles as if bowing to one another. Nothing leaps, nothing snaps, and yet everything changes. The solar system breathes. Physicists give these motions precise names. When the long axis of an elliptical orbit turns, the turning is apsidal precession, the perihelion slowly migrating around the Sun. When the orbital plane itself nods up and down relative to the ecliptic, that is nodal precession, the line where the plane crosses the ecliptic sliding like a compass needle that never quite rests. Layer these together for every planet, and you get a choreography of cycles, some measured in tens of thousands of years, some in millions that overlap like waves on a very calm sea. You already live inside one of these rhythms, Earth's perihelion. The point where we are closest to the Sun does not always align with the same season. It slowly precesses, completing a circuit in roughly 100,110 years. Our axis also wobbles in axial precession, taking about 26,000 years to trace a circle against the stars, and the tilt itself gently oscillates obliquity cycles, as does the shape of the orbit eccentricity cycles. These are the Milankovitch rhythms that pace the waxing and waning of ice. But beneath these familiar beats lies a deeper orchestration, the way every planet's gravity whispers to every other, trading tiny quanta of angle and eccentricity in an endless conservative exchange. Mathematically, you can think of the solar system as a set of coupled pendulums, each planet, a pendulum each coupling a gravitational whisper. In the language of classical celestial mechanics, the slow rotations of the perihelia are described by secular eigenmodes often labelled G1, G2, G1, G6, Jundots G1, G2, while the nodal tilts follow system modes S1, S2, Z1, S2, and Dots S1, S2. Each mode is a pure tone. Each planet is a chord, a sum of tones at different volumes. Jupiter's apsidal tone, often associated with G5, G5, G5 rings, loudest setting the baseline. Saturn's follows close behind. The inner planets carry fainter, quicker notes that beat against the giant's deep hum. Sometimes these beats align to make a visible change. Sometimes they cancel into near stillness. You do not hear it with your ears, but you can see it in rock and ice, and the slow drift of orbital elements over geological time. This is the breathing symphony. Precession is not just a curiosity, it is architecture maintenance. Left untouched, gravitational tugs would eventually pile up into dangerous alignments. Precessions disperse those tugs over directions and timescales, like a building that sways in the wind by design so it will not crack. Mercury's perihelion, famous for its extra 43 arc-seconds per century of precession from general relativity, is a reminder that even the Sun's curved spacetime participates in the metronome. At the other extreme, Neptune and the Kuiper Belt exchange slower, statelier nods, their planes shifting so gradually that a human civilization could rise and fall without noticing a degree of change. There is a temptation to imagine this breathing as precarious, a delicate balance doomed to fail. The modern picture is subtler and kinder, with today's N-body integrations numerical experiments that compute the gravitational dance of all the planets with high fidelity. We can let a digital solar system run for hundreds of millions of simulated years. What we see is not a frozen machine nor a chaotic collapse, but bounded restlessness. The inner planets are chaotic in a technical sense. Their exact angles become unpredictable beyond tens of millions of years because tiny uncertainties grow, but their energies and distances remain corralled. The outer planets are even more sedate, their long low-frequency modes acting like stabilizing anchors. On billion-year scales, improbable events can occur. Mercury's orbit, for instance, has a vanishingly small chance of wandering into deep trouble. Yet the overwhelming story is resilience motion that never stops, structure that never fails. Why so resilient? Because precession spreads risk. Consider Earth and Venus. Their perihelia do not aim at one another for long. Each is rotating on its own clock, so any one alignment dissolves into a different geometry before gravity can push too hard. Secular resonances, the long-term commensurabilities between those acidal and nodal tones, do exist, and can pump inclinations or eccentricities if they capture a planet or a belt of debris. But most of the time the resonance passes like a tide, transferring a little energy and moving on. The system bends, it does not break. This bending is visible even in the asteroid belt. Regions called Kirkwood gaps are carved where asteroids feel repeated. Nudges mean motion resonances with Jupiter that trade speed for safety until an asteroid's orbit is altered enough to leave the gap behind. More subtle still are the secular resonances that lift or lower asteroid inclinations over tens of millions of years, painting the belt with families and streams. In the Kuiper Belt, Pluto and its kin trace inclined elongated paths protected by resonance with Neptune. Their perihelia precess in phase relationships that prevent close approaches. You could call it luck, but it is really the emergent property of many cycles sharing space, the way polyphony makes music from potential dissonance. Look outward for corroboration, and new telescopes oblige. Infrared views of Beta Pictoris resolve a razor-thin debris disk whose inner regions show slight warp signatures of embedded planets, processing the dust. In other young systems, concentric rings are subtly misaligned, like a stack of records with their labels rotated, implying that nodal precession is already at work while planets still grow. The same physics that keeps our ecliptic nearly flat yet gently wavy seems to be a universal habit of rotating self-gravitating systems, not perfection, but disciplined variation. There is poetry here, but it comes from math that refuses to be sentimental. Each precession rate depends on masses, distances, and geometry. Change anyone and the breathing shifts tempo. Over deep time, the sun itself evolves, losing mass to the solar wind and light. That too imperceptibly changes the score-lengthening orbital periods by slivers. Passing stars and the galaxy's tidal field add notes at the very lowest frequencies, almost too slow to count, bending the distant Oort cloud and modulating comet deliveries. Even those whispers are integrated into the symphony without breaking it. Stable does not mean static, and chaotic does not mean doomed. The lesson of modern integrations is that a system can be both sensitive in detail, robust in structure. You can predict the exact date of next winter, but not the exact snowflake. You can forecast the band of Earth's climatic future, but not the day of its next storm. On the scale of worlds, precession is the quiet averaging that makes prediction possible, the reason the seasons repeat ice ages cycle, and the sky's wandering lights continue to return along the same narrow band. If you could watch from high above the sun's north pole accelerating time until planets stitched glowing threads, you would see each ellipse slowly turning like petals, opening and closing, each orbital plane tipping and righting in prolonged bows. The inner threads would shimmer with fine quick ripples. The outer threads would pulse with long, slow swells. Now and then the patterns would align beats in unison, a deep chord, and then drift apart again. No conductor lifts a baton. No hand corrects the page. The score writes itself in gravity and motion, and the orchestra remembers. This then is the breath of the solar system cycles within cycles, the slow wheeling of ellipses and planes that converts peril into pattern. What began as a collapsing storm learned restraint. What could have unraveled learned to precess. The result is a living calm. We stand inside it without feeling the sway our years counted by a heartbeat we cannot hear, and yet the ear grows curious. If the system breathes, what about the outliers, the sideways spinners and backward dancers who test the rule? The next movement belongs to rebels Venus and Uranus, whose rotations defy the prevailing wind and the captured moons and retrograde asteroids that sketch counter-melodies against the main theme. How can discord live inside such order and still leave the music whole? Look down from far above the sun's north pole, and you'll notice a remarkable unanimity. Every planet, every major moon, every grain of dust in the inner system moves counterclockwise. The asteroids glide that way, the comets of short period loop inward and outward along that same sense of motion. Even the solar wind itself spirals out in that direction. It's not coincidence, and it's not preference. It's memory. The solar system still spins the way it was born to spin. More than 4.5 billion years ago, the solar nebula, the cloud that would become everything we know, carried a faint rotation, a slow swirl inherited from the larger molecular cloud out of which it collapsed. In space, there is no such thing as absolute stillness. Every fragment of matter moves drawn by gravity, nudged by passing stars, stirred by the rotation of the galaxy itself. Our patch of that galactic cloud happened to be turning one way counterclockwise when seen from the direction that later became north. When gravity began to draw that cloud inward, angular momentum demanded that the spin accelerate. The inward fall became rotation, the rotation became flattening, and the flattening became a disk. That original twist, tiny in the beginning, was stretched and preserved as everything condensed. The sun itself formed from the densest center of that whirl, capturing most of the mass, but not all of the spin. The remaining angular momentum stayed in the disk, expressed as the orbits of planets circling one direction around their newborn star. To reverse that motion, you would have to reverse time itself. Every molecule, every grain, every flow of gas would have had to collide in perfect antisymmetry. Nature does not waste such miracles. The rule was set in the first rotation, and all later structures simply inherited it. Even the sun's rotation is an echo of that primordial spin. It turns once every 25 days at its equator, about 35 days near the poles, is plasma flowing like syrup stirred unevenly in a pot. That difference, differential rotation, is the heart of solar magnetism. The sun's magnetic field lines frozen into the conducting plasma are wound up by the rotation into a coiled pattern that extends through the solar wind. That pattern is known as the Parker spiral, named for astrophysicist Eugene Parker, who first described it in 1958. Because the solar wind escapes at supersonic speeds, while the sun continues to rotate, the magnetic field lines stretch outward into space as elegant spiral arms like the jets of water flung from a rotating sprinkler. Seen from above the North Pole, those spirals twist counterclockwise the same direction as the planetary orbits. They are the magnetic handwriting of the same ancient motion. The Parker spiral is not just a visual curiosity. It shapes the heliosphere, the vast bubble carved in the interstellar medium by the sun's wind. Charged particles, cosmic rays, even interplanetary dust all feel its guidance. Every aurora on Earth, every whisper of radio emission from Jupiter's magnetosphere is connected by those curling field lines back to the sun's rotation. The entire solar system, electrically speaking, is wired along the same twist. Magnetohydrodynamics, the study of how magnetic fields and conducting fluids interact, reveals why this coherence persists. The plasma in the sun and the solar wind behaves as a fluid threaded by invisible lines of magnetism. In such a system, the field lines are frozen in, they move with the fluid, conserving the topology of the magnetic structure. When the sun rotates, the plasma carries the magnetic lines with it, and because the wind carries them outward faster than light can rearrange them, they freeze into spirals rather than straight lines. The solar wind becomes an enormous rotating extension of the sun itself, a slow-turning wheel of magnetized breath. This magnetized rotation helps sustain the counterclockwise legacy. The magnetic torque exerted on the disk during its early life transferred angular momentum outward. The sun spun slightly slower, the planets gained orbital energy, and the whole system settled into its present configuration. Today, spacecraft like NASA's Parker Solar Probe and ESA's Solar Orbiter measure this structure directly flying through regions where the magnetic field reverses polarity every 11 years as the solar cycle renews itself. Each flip, each gust is still counterclockwise at its root. The universe, once set in motion, keeps turning the same way. The persistence of this shared direction is not confined to our system. Across the galaxy, young stellar disks imaged by ALMA and JWST show the same inheritance. Each one spins the way its parent cloud turned. Each carries forward angular momentum carved from local turbulence and galactic rotation. Half spin one way, half the other, depending on the randomness of their birth. There is no cosmic right or left, only the memory of initial conditions. In our corner of the Milky Way, the dice happen to land on counterclockwise. If you could trace the spiral arms of our galaxy themselves, you'd find the same principle writ large. The Milky Way's rotation gives its clouds a preferred sense of spin, a bias that threads down into the scales of stars and planets. Every level of structure inherits a portion of motion from the level above. Galaxies spin, clouds within galaxies spin, stars within clouds spin, planets around stars spin. The cosmos is a cascade of angular memory, each generation borrowing its direction from its parent. It's easy to overlook how deeply this one fact shapes our existence. Because all planets orbit in roughly the same direction, they rarely collide. Their gravitational tugs remain orderly, producing long-term stability instead of chaos. Our moon rises and sets in harmony with this motion. Our days and years align because the spin of Earth itself reflects that same cosmic bias. Even the path of interplanetary spacecraft must respect the inherited direction. Rockets launch eastward, using Earth's rotation to gain a small but vital push from the ancient spin that began it all. The entire structure of our sky, the way the planets trace a single band across the heavens, is the visible trace of that first swirl. Every sunrise, every season, every familiar pattern of return follows from it. The solar system's unity of direction is not merely a curiosity of physics, it's a condition for habitability, a geometric piece built from ancient motion. In a sense, the solar system is a fossil gyroscope. Its counterclockwise spin stabilizes everything within it, maintaining orientation, even as the sun orbits the galaxy, even as external forces tug. The constancy of direction is a reminder that time moves forward while motion remembers backward. Every world circling the sun carries the whisper of a long-dead cloud's rotation, a gesture frozen in gravity. Yet not all worlds obey perfectly. Some spin the other way, some roll on their sides. Venus, Uranus, and a handful of captured moons remind us that memory can be interrupted, rewritten by catastrophe. But even their rebellions are measured against this one fundamental rule. Counterclockwise is the baseline, the legacy, the original agreement between matter and motion. And so, when you look up tonight and see the planets threading along the same path through the stars, you're watching the direction of creation itself, a single gesture repeated endlessly from the swirl of plasma around the sun to the curl of magnetic fields across interplanetary space. The universe began to turn, and it never stopped. The sun breathes that rotation into every gust of solar wind. The planets keep time with it. The comets carry it to the edge of the heliosphere. The solar system, still counterclockwise after billions of years, is a living fossil of the first spinner record that never ceased playing. Next, we'll explore how that ancient inheritance is recorded not only in the sun's motion, but in the spin of every world itself, some faithful, some defiant, and what their rotations reveal about the violence and creativity of the system's youth. If you look at the sun through a telescope carefully filtered the way Galileo first did in the 17th century, you will see dark, shifting stains gliding across its face. They are sunspots, temporary islands of magnetism cooler than their surroundings, and they drift in a single direction. Galileo noted that they move from east to west, taking about 4 weeks to cross the solar disk. From that observation, he deduced something astonishing: the sun itself rotates. It was our first clue that even the star anchoring the solar system carries memory and motion. The sun turns once every 25 days at the equator, and about 35 days near the poles. That difference, called differential rotation, is not a flaw, but a feature of its nature as a sphere of plasma rather than a solid body. Layers slide over one another like glowing syrup stirred by invisible hands. Deep inside in the tachocline, a boundary between the radiative interior and the convective envelope, this shearing motion twists magnetic field lines like stretched rubber bands. When those lines snap and reconnect, they erupt as sunspots flares, and coronal mass ejections, the solar heartbeat that shapes space weather across the system. But beneath every storm and flare lies something older: the direction. The sun spins counterclockwise exactly as the planets orbit. It never forgot how it was born. The principle of conservation of angular momentum ensures this continuity. The star formed at the center of a rotating nebula, absorbing its mass and its spin. Even as the disk around it fragmented into planets, the sun retained the rotational sense of that primordial cloud. And while the planets orbit because of that shared momentum, the sun's internal rotation anchors the pattern. Its equator, nearly aligned with the ecliptic, testifies to that common birth. If the solar system is a dance, the sun is both stage and dancer, the largest participant yet, still moving to the same cosmic rhythm. For centuries we could only infer this rotation from the movement of sunspots. Then in the 20th century, spectroscopy and Doppler measurements confirmed it. One limb of the sun shifts slightly toward us, the other away, revealing the same counterclockwise spin. Today, spacecraft have turned inference into direct observation. The Solar and Heliospheric Observatory SOHO, launched in 1995, then monitored the sun's oscillations, tiny ripples on its surface, to map how fast it spins at different depths. The results showed a complex symphony of layers, fast equator, slow poles, twisting magnetic flows. Then came NASA's Parker Solar Probe, a craft that dives closer to the sun than any in history, sampling the solar wind itself. Each time it loops around, it detects the magnetic field lines that spiral outward, evidence that the sun's rotation extends far beyond its surface. The probe's instruments record the same pattern Eugene Parker predicted decades ago, a vast Parker spiral sweeping counterclockwise through the solar system. It's the sun's magnetic breath still curling in the direction it first learned 4.6 billion years ago. Even farther out, Voyager 1 and 2 confirmed that the magnetic field continues this twist at the edge of the heliosphere. The sun's rotation encoded in magnetism still reaches into interstellar space. Motion once begun has become history written in plasma. But the story doesn't end with the sun. Our entire system, the sun and its planets together, moves within a greater current. The Milky Way galaxy itself spins a vast disk of hundreds of billions of stars orbiting a dark gravitational center. The sun is one of those stars located about 27,000 light-years from the galactic core. It travels around that center at roughly 220 kilometers per second, completing one circuit every 230 million years. We are midway through our orbit, a half-revolution since the age of dinosaurs. From a galactic vantage, the entire solar system resembles a single bead Caught in another cosmic spiral, the sun's counterclockwise spin and the planet's orbits are nested motions within the galaxy's rotation like eddies in a vast slow river. Angular momentum flows downward through scales from the Milky Way's rotation to the cloud that spawned the sun, from the sun to its disk, from the disk to the planets. Motion begets motion, direction begets direction. This hierarchy of movement means that when we speak of the sun standing still, we're indulging an illusion. Even at rest on Earth, we're racing through space spinning eastward, with the planet's rotation circling the sun at 30 kilometers per second and hurtling with the sun around the galactic center at nearly 500,000 miles per hour. And beyond that, the Milky Way itself drifts through intergalactic space toward the Virgo cluster, its own orbital destiny. Every level of structure inherits the inertia of the one before it. Our local spin is just one stanza in the great poem of motion. Manita hydrodynamic models show that such nested rotations reinforce one another. The galaxy's rotation creates large-scale magnetic fields that thread its spiral arms. Inside those arms, molecular clouds form and collapse, already twisted by those fields. When a portion of the cloud condenses into a new star, the orientation of its magnetic field and its spin often reflect the larger field's direction. Motion propagates like inheritance, not rigidly aligned, but statistically biased, as if the cosmos preferred continuity. Astronomers now use Gaia data to map the orbits of nearby stars, discovering that many move in streaming groups, stellar families born from the same rotating cloud, still traveling together millions of years later. The Sun may be a member of one such dispersed family, the ancient remnant of a cluster that formed in the same galactic whirl. Its motion through the galaxy is not solitary, it's collective, another layer of shared memory. So when you trace the Sun's slow roll across the sky, or feel the eastward tug of Earth's spin in the launch of a rocket, you are sensing a thread that runs through every level of cosmic structure. From Galileo's first glimpse of moving sunspots to Parker's measurements of spiraling magnetism, every observation reveals the same truth: motion is memory. The Sun does not merely rotate, it remembers the direction of its birth cloud. The solar wind does not merely blow, it carries that rotation outward. The planets do not merely orbit, they repeat the same gesture around the same axis. Even the galaxy's slow spin sustains this continuity, a cascade of momentum preserved through scales and epochs. In physics, angular momentum is conserved. In poetry, it is inheritance. The universe forgets many things, heat dissipates, structures decay, but it never forgets a turn once begun. Every revolution of the Sun, every orbit of Earth, every swirl of gas in the distant arms of the Milky Way is a recitation of the first spin that set us all in motion. We are quite literally travelers riding on memory, drifting within a spiral that began before there was light to see it, and will continue long after the last flame of the Sun has gone out. From a distance, the solar system appears serene, a clockwork gliding in silence. The planets trace their paths with exquisite precision, each orbit repeating each revolution measured to the second. Mercury darts ahead, Earth hums in the middle gears, Jupiter turns like a great slow wheel, and Neptune, far out on the rim, completes the motion in patient decades of centuries. Seen whole, it resembles a vast coherent machine, the greatest kinetic sculpture in existence. But what looks like peace is really the truce after a storm. 4.5 billion years ago, this cosmic clock was not calm but chaotic. The newly ignited sun blazed amid a whirl of shattered rock vapor and molten rain. Planetary embryos crashed and merged, atmospheres boiled away and recondensed, debris ricocheted through the disk like shrapnel. The faint symmetry we see today was carved from violence disciplined by time. Each collision was a negotiation of momentum. Worlds were hammered into shape, then rounded by their own gravity. Orbits, once erratic, were smoothed by billions of encounters until they fell into near-circular coplanar grace. What we now call order is the visible fossil of equilibrium reached through destruction. The same collisions that could annihilate a world also refined its path, adjusting speeds and tilts until the system's energy balanced like a self-correcting mechanism. Imagine a clockmaker at work, not with tools but with impact and flame. Jupiter, the giant gear, holds the balance wheel. Its gravity regulates the smaller bodies the way a pendulum steadies time. Earth and Mars glide like meshed cogs, each rotation driving the other's resonance. Even the asteroids act as the clock's escapement, ticking off intervals through collision and alignment. It is a delicate synchrony built on the principle that motion shared is stability gained. The precision of this mechanism remains astonishing. Astronomers can predict planetary positions thousands of years into the future, with errors measured in seconds of arc. The same equations that guided Voyager through the gravitational keyholes of Jupiter and Saturn ensure eclipses and transits repeat with mathematical inevitability. In every sense that matters, the solar system functions like a cosmic timepiece, ruined by gravity and never allowed to run down. But that piece is relative. Beneath the clock's smooth, ticking turbulence still hums. Each orbit precesses, each axis wobbles, each resonance subtly shifts. The system is stable but not static. It's alive with adjustments constantly tuning itself to preserve harmony. The clock corrects itself while it runs. Modern simulations show this stability is statistical, not absolute. The inner planets sensitive to small perturbations may wander by fractions of a degree over hundreds of millions of years, like tiny gears vibrating in their sockets. Even that jitter is part of the balance, a buffer that absorbs chaos instead of amplifying it. The grand design endures precisely because it tolerates imperfection. The solar system's beauty lies in its elasticity, not its rigidity. If you could look beneath the orbits, you would see an invisible architecture of energy flows. Each planet stores angular momentum, exchanging it with its neighbors through subtle resonances, trades so faint they take millennia to complete. The result is a vast gyroscopic network in which every body contributes to the overall equilibrium. Jupiter's pull stabilizes Earth's orbit against wild eccentricities. Saturn's resonance prevents Neptune from drifting into the Kuiper belt. Even the asteroid belt's fragmented masses participate their collective gravity, adding friction to the system's evolution, damping wild oscillations. It's as though each planet hums a note in a symphony that keeps the others in tune. The entire system is a harmonic oscillator, a self-regulating engine that turns chaos into continuity. Carl Sagan once described it as the music of spheres, an ancient metaphor revived by mathematics. What he meant was not mysticism, but resonance. The realization that celestial mechanics is harmony, soundless, exact, and continuous. The solar system breathes in the rhythm of physics, and every rotation is a verse in its song. Yet no machine, however perfect, is without eccentricity. Not all the gears fit their sockets neatly. Not every world spins in obedience to the common current. Within this grand clockwork, two planets break the rule entirely. They turn the wrong way. Venus, wrapped in its thick golden cloud, spins backwards so slowly that its day lasts longer than its year. The sun rises in the west and sets in the east, a defiance of the system's inherited motion. Uranus, distant and strange, rolls on its side, its axis tilted by almost 98 degrees. It doesn't so much rotate as tumble its poles, taking turns facing the sun in seasons that last 40 years. These are the rebels of rotation, the imperfections that reveal the machine's history. Their disobedience is not an error in design, but a memory of violence, a record of titanic impacts, tidal talks, and atmospheric struggles that once nearly broke the system before it healed. Their backward and sideways motions whisper of a time when the clock had no rhythm at all, when gravity's gears were grinding themselves into alignment. That they still exist, still orbiting peacefully in the same counterclockwise flow, shows how robust the system truly is. The cosmic machine tolerates dissent. It folds even rebellion into order. So when you gaze at the planets and imagine serenity, remember what you are seeing is not peace but equilibrium after fire. The solar system is a clock that forged itself in collision, learned to tick from chaos, and still keeps time against entropy's pull. Its hands turn counterclockwise because that's the direction of its birth, its memory encoded in every orbit. But inside that coherence lie stories of resistance, the worlds that refuse to spin the same way. And to understand them is to glimpse how fragile this order once was. Next, we'll turn the camera toward those two outliers, Venus and Uranus, and watch how impact, atmosphere, and chance rewrote their destinies, leaving them forever dancing against the current of the sun. If every world is a memory of the solar system's birth, then Venus is the memory that hesitated. From far away it looks like Earth's twin, almost the same size, the same mass, the same glow. But approach through its golden clouds and you find a paradox. The entire planet is turning backward. On Venus, the sun rises in the west and sets in the east, and it does so excruciatingly slowly. One full rotation of Venus takes 243 Earth days, but it completes its orbit around the sun in only 225 days. That means a single day on Venus is longer than its year. The planet's atmosphere, its geology, even its magnetic field whisper the same question. How does a twin of Earth end up spinning against the current of creation? To understand this rebellion, we must first remember that Venus began, like all the others, born from the counterclockwise swirl of the solar nebula. Its initial rotation was likely prograde, turning the same way it orbited as conservation of angular momentum would predict. But somewhere in the first 100 million years, that inherited spin began to falter. Two great theories compete to explain what happened. Theory 1, the catastrophic collision. In the early solar system, the space between planets was crowded with planetary embryos, worlds the size of the Moon or Mars, each tracing eccentric orbits through a sea of debris. Collisions were routine and often apocalyptic. According to one idea, Venus was struck by a giant impactor, perhaps half its size, glancing rather than head-on. Such a collision could have inverted its rotation without destroying the planet. The aftermath would have been a molten ocean of rock and iron, its angular momentum flipped. Over time, as the surface cooled, the reversed spin stabilized, locking the planet into its present languid rotation. This hypothesis explains the direction, but not the slowness. An impact violent enough to reverse spin would likely have left Venus spinning rapidly the other way, not barely turning at all. Something else must have slowed it down. Theory 2, the atmospheric torque. Venus's atmosphere is not a veil, it's a weight. The air pressure at its surface is 90 times that of Earth's. Its clouds are thick enough to hide the surface permanently, and they swirl with hurricane winds that circle the planet in just 4 Earth days. Those winds generate immense friction between the atmosphere and the solid planet below. Over billions of years, this drag combined with tidal forces from the Sun may have braked Venus's rotation until it halted and then reversed. Computer models in the last 2 decades have shown that a planet with a dense atmosphere and no large moon like Venus can indeed slow its spin drastically. Once near standstill, tiny asymmetries in solar tides, minute differences between morning and evening heating can tip the balance into retrograde. The planet then locks into a slow equilibrium, turning backward just fast enough to keep those tidal torques balanced. It is a delicate tug of war between the Sun's gravity and the air's inertia. Venus spins the wrong way because paradoxically it found stability in reversal. Recent radar mapping from missions like Magellan and Venus Express, and new data from Japan's Akatsuki orbiter reveal that the planet's rotation rate is still changing by fractions of a second per year. Tiny shifts caused by exchanges of angular momentum between the atmosphere and the solid globe. Venus is not frozen, it's still negotiating with its own air. The atmosphere behaves almost as a second planet, one body made of gas, one of stone turning in near opposition but bound together. The result is a slow dance where the clouds lap the surface 60 times faster than the planet itself rotates. From orbit, you'd see cloud patterns racing eastward, while the planet beneath drifts westward, a perpetual wind chime in slow motion. For all its physics, Venus's backward spin has always stirred the human imagination. In ancient myth, Venus was never just a planet, it was the morning and evening star, the symbol of beauty, desire, and the cycles of light and love. Yet beneath that poetic identity lies a world where day and night last 4 months each, and the sun rises where it should set. Imagine standing if you could survive the heat on the surface of Venus under a yellow sky, thick with sulfur clouds. You'd see the sun, a pale orange glow through the haze, crawl up from the western horizon. It would take weeks to climb hover overhead for months, and then slide down toward the east, sinking into a horizon you'd barely recognize. Your shadow would drift in the opposite direction from everything you've ever known. Time itself would seem reversed. Perhaps it's fitting that a planet named for love, the most unpredictable of forces, refused to follow the rule. In a solar system built on coherence, Venus is the first great descent. Its backward rotation reminds us that the machine we call orderly is more resilient than rigid. It can absorb rebellion, fold it into the harmony, and still keep turning. Venus orbits in the same counterclockwise path as all the others, but its surface whispers another rhythm, a private heartbeat that runs against the tide. The sun's magnetic breath still wraps around it in the Parker spiral, flowing east to west while the clouds beneath push west to east. Between them lies the paradox of motion and memory, the planet that turns backward but still belongs to the same design. And yet even Venus's defiance feels modest compared to the next story, the planet that didn't merely turn backward but fell entirely onto its side, spinning like a rolling world adrift in the dark. Next, we meet Uranus, the planet that never learned which way is up. From the edge of the outer darkness comes a world that seems to have lost its balance. Uranus, pale, distant, ghostly blue, is the planet that fell sideways. While all other worlds spin like tops upright enough to face the sun in a predictable rhythm, Uranus rolls like a marble on its orbit, its poles taking turns pointing toward the light. Its tilt is a staggering 98 degrees, so extreme that it seems to orbit on its side. For half of its 84-year journey around the sun, one hemisphere basks in unending day, while the other sinks into decades of darkness. It is a planet that does not so much rotate as revolve through solitude. When Voyager 2 flew past Uranus in January 1986, the only spacecraft ever to visit it found a world of contradictions. The planet was calm, almost eerily featureless, with a faint banded atmosphere and a ring system so dark it nearly disappeared against space. Its magnetic field was tilted 60 degrees from its spin axis, and displaced from the planet's center an impossible geometry, like a compass that forgot where north was. The data suggested an internal structure out of alignment, a world whose very magnetism had been twisted by catastrophe. For decades, that was the mystery. What could have knocked a planet over? At Durham University in England, astrophysicists built supercomputer models to reconstruct the violence of Uranus's youth. Using high-resolution smoothed particle hydrodynamic simulations, they tested collision after collision, massive protoplanets slamming together in the early solar system, each impact reshaping a world. Their findings were stark. Uranus likely suffered a giant impact with an object 1 to 3 times the mass of Earth. The collision was not head-on, but glancing a slow-motion cosmic body check that delivered enough angular momentum to tip the entire planet on its side without destroying it. The energy from that event could have vaporized part of the protoplanet's icy mantle, forming a disk of debris that later condensed into the planet's faint dark rings. Some simulations even suggest multiple smaller strikes, each nudging the axis further, until the planet toppled completely, a cumulative surrender to chaos. The catastrophe would have had long-lived consequences. The impactor's dense core may have merged imperfectly with Uranus's, leaving the magnetic field offset. Heat trapped in the aftermath could explain why Uranus, unlike Neptune, radiates so little internal energy today. It is a world still chilled by trauma, a planet that hides its past beneath a placid mask. The planet's sideways stance also reshaped its seasons in surreal ways. When Uranus's north pole faces the sun, it remains in daylight for 42 Earth years, while the south pole freezes in unending night. Half an orbit later, the roles reverse. At the equinox, sunlight slides briefly along the equator, throwing the atmosphere into turbulent transitions. Voyager's instruments caught this world in the depths of southern summer, an eerily uniform blue sphere. But as telescopes on Earth continued to watch, the planet began to awaken. By the 2000s, infrared imaging from the Keck Observatory and later the James Webb Space Telescope revealed shifting band storms and bright polar caps of methane haze. JWST's NIRCam instruments mapped Uranus's atmosphere in unprecedented detail, showing cloud systems building near the illuminated pole, while the dark hemisphere cooled and slept. The slow rotation, about 17 hours, still counterclockwise relative to its own tilted axis, keeps these patterns in constant twilight, a planet forever turning between extremes of night and day. To see Uranus in infrared is to glimpse a ghost of heat, a faint memory of formation still leaking through ice and cloud. Beneath the upper atmosphere lies a mantle of water, ammonia and methane ices, under crushing pressure, an ice giant in name and truth. Its calm appearance belies the dynamism beneath swirling convective cells, lightning deep in the cloud decks and the silent churn of a world that once rolled over and never stood up again. Emotionally, Uranus feels like the loneliest planet, a survivor of impact that never returned to alignment. Where Jupiter thunders and Saturn shines with golden storms, Uranus drifts in quiet blue-green, its axis leaning as though in mourning. It rolls along the edge of the sun's light, obedient to the orbit but indifferent to the rules of spin. You could say it's still falling forever, falling sideways around the sun, caught in the same motion that toppled it billions of years ago. If you could stand on its icy clouds, impossible. But imagine you'd see the sun tracing a circle near the horizon, neither rising nor setting, just looping endlessly through the sky. Seasons would last a lifetime. Dawn and dusk would blur into one another. The planet's day would be a dream of rotation, neither day nor night, just a slow roll through eternity. And yet even Uranus's defiance fits within the grand harmony of the solar system. Its orbit remains nearly circular, its moons move in perfect synchrony with its tilt, and its rings follow the same sideways geometry as if the entire miniature system accepted the new orientation without protest. The cosmic clock adjusted its gears to include a wheel that spins the wrong way, and the rhythm endured. In this sense, Uranus is not a broken planet, but a proof of resilience, a world that absorbed catastrophe and kept turning. It embodies the paradox of the solar system itself, motion born of violent stability sculpted by chaos. We often imagine the heavens as calm, but every orbit, every tilt, every ring is the echo of an ancient blow that the universe chose not to erase. Uranus, the fallen world, simply wears its scar more visibly than the rest. As Voyager 2's cameras receded, they captured one last image of the planet shrinking into darkness, its axis tilted almost flat to the frame, its pale light fading against the black. That image remains one of the most haunting portraits in all of planetary science, a world that fell over billions of years ago and never rose again, rolling endlessly through the cold. Next, we'll turn to how the rest of the solar system embraced such disorder. How moons, spins and tides adjusted around the oddities of Venus and Uranus to preserve the overall harmony. Even chaos, it seems, can be tuned. In every family there are outliers, the ones who took a different path, whose choices remind the others what could have been. In the solar system, those outliers are Venus and Uranus. One spins backward, the other sideways, and between them, they carry a truth deeper than any equation that even in a universe governed by law, difference survives. Venus, the planet that turned back, and Uranus, the planet that fell, are not accidents in isolation. They are survivors of the same violent childhood that shaped every world. Each began as an obedient child of the solar nebula, spinning counterclockwise like Earth, Mars, and the rest. But somewhere along the way, chance intervened. On Venus, the catastrophe was drawn out, an atmospheric tug-of-war, perhaps a glancing impact slowly reversing a rotation until sunrise appeared on the wrong horizon. On Uranus, it was instantaneous, a collision so immense that it rolled an entire planet over, leaving its poles pointing where its equator once was. And yet both planets, even after their rebellion, still orbit the Sun in the same counterclockwise direction as all the others. Their rotations may have changed, but their orbits did not. That is the key distinction between spin and revolution, between the personal motion of a world and the collective motion of the system. A planet's rotation can be rewritten by collision, by tides, by atmospheric drag. But the path it takes around the Sun is harder to erase, locked by the angular momentum of the entire solar family. Rotation is identity. Orbit is ancestry. Earth too bears a scar from that turbulent age, a reminder that the line between order and chaos is razor thin. About 4.5 billion years ago, our planet was struck by a Mars-sized body now called Theia. The impact nearly destroyed Earth, but instead reshaped it, melting much of the crust and launching a torrent of debris into orbit that coalesced into the Moon. The blow tilted Earth's axis to about 23.5 degrees, giving us seasons. It sped up our rotation, shortening the primordial day to a few hours. Over billions of years, the gravitational pull of the Moon has gradually slowed that spin to the 24-hour rhythm we know. Without that impact, there might be no Moon, no tides, no gentle regulation of climate. A single catastrophic collision created the conditions for stability, the same paradox we see in Venus and Uranus, though their consequences were more extreme. 3 worlds, 3 different responses to chaos. Venus found equilibrium in reversal. Earth turned violence into partnership. Uranus fell and kept rolling. Together they traced the full spectrum of cosmic adaptation, the ways matter learns to endure what physics demands. When we compare them, a pattern emerges. Rotation is fragile. Orbit is faithful. Collisions, tides, and atmosphere can flip or slow a planet's spin, but the vast angular momentum of the solar system's counterclockwise flow remains untouched. It's as if the system carries a deeper memory, one immune to local trauma. The planets may forget their spin, but the Sun remembers their path. That resilience is what keeps the solar system coherent. Each world can suffer catastrophe and still be drawn back into the rhythm. Each deviation adds character, but not collapse. In the quiet of modern observation, this is easy to forget. We see a calm sky and imagine it was always so. But every rotation, every tilt, every breeze that brushes your skin began in violence and inheritance of collision. The same physics that broke symmetry also built balance. fragility and resilience. It turns out are the same phenomenon seen from opposite sides of time. This coexistence of difference and order gives the solar system its personality. It's not a factory of identical worlds, but a gallery of survivors. Mercury's scorched metal, Jupiter's perpetual storms, Saturn's icy rings, Neptune's howling winds, and the rebels Venus and Uranus, who remind us that rules in nature are habits, not absolutes. When you look across that diversity, the pattern is not perfect harmony, but tolerant harmony. Each planet is allowed to remember its trauma in its own way, and yet the ensemble holds together. That's the secret of longevity, not rigidity, but adaptability. The universe's perfection is not in symmetry, but in persistence. In recent years, computer models and data from missions like Parker's Solar Probe, Juno Akatsuki, and JWST have deepened that lesson. They show a solar system that still flexes, still breathes, orbits, precessing tilts, wobbling rotations, evolving. Stability is maintained not by stillness, but by constant adjustment. The coherence we admire from afar is the sum of countless small corrections, a self-balancing dance that absorbs imperfection without losing rhythm. It's a humbling image. Even the most ancient motions are negotiations, not commandments. Gravity doesn't demand obedience, it invites compromise. And through those compromises, individuality endures. Venus glows in defiance, Uranus rolls in silence, and Earth spins with purpose, all three held in the same counterclockwise embrace, the sun's original gesture still echoing through their paths. So when you see the morning star rise before dawn or picture that turquoise planet tumbling through the dark, remember what they represent, not error, but evolution. The solar system is not a perfect machine, it's a community of survivors, each with its own rhythm, each carrying scars that became structure. Even the heavens allow for difference. Even chaos given time learns to belong. Next, we will bring these stories together, how the unity of direction, the persistence of orbit, and the forgiveness of variation combine into something greater than mechanics, a cosmic identity that remembers where it came from and never stops moving forward. If the planets are children of the sun, then the moons are the grandchildren born from smaller disks that spun around their parent worlds, inheriting their rhythm, just as the planets inherited the suns. Each great planet carries its own miniature solar system, complete with orbits, tilts, and resonances, all following the same ancestral rule. Motion is inherited. When a planet grows massive enough, especially a gas giant like Jupiter or Saturn, its gravity gathers a swarm of gas, ice, and dust into a circumplanetary disk. Within that glowing halo, particles collide, clump, and flatten into a smaller version of the solar nebula. And just as the sun's nebula turned counterclockwise, so too do these planetary disks. Their spin reflects the same direction as the planet's rotation, because both are carved from the same angular momentum. From this swirl emerge regular moons worlds that form in circular equatorial orbits, moving the same way their planet spins. They are miniature echoes of the solar system itself, calm after violent harmony reborn on a smaller scale. Consider Jupiter, the archetype of inheritance. Around it circle four great spheres discovered by Galileo in 1610 through a crude telescope, but now mapped in exquisite detail by the Juno spacecraft Io, the volcanic furnace molten with perpetual tides. Europa smooth and bright, its icy shell hiding a global ocean. Ganymede, the largest moon in the solar system with its own magnetic field. Callisto, ancient and created a record of everything the others forgot. All four orbit in the planet's equatorial plane, all counterclockwise when viewed from Jupiter's north pole, and all locked in a gravitational resonance so elegant it could be written as music. For every four orbits of Io Europa completes 2 and Ganymede 1. This Laplace resonance keeps their orbits stable and their interiors alive. The pull between them stretches and kneads their cores, driving heat volcanoes and possibly life beneath the ice. The Jovian system is a microcosm of the Sun's family, a central furnace surrounded by worlds of rock, water, and possibility, all held in counterclockwise obedience. Beyond Jupiter lies Saturn, lord of rings and rhythm. Its greatest moon, Triton, is a world so large it rivals Mercury, and carries its own thick atmosphere of nitrogen and methane. Triton orbits in the same direction as Saturn's rotation, counterclockwise and equatorial, exactly as theory predicts. It too was born from a circumplanetary disk, ice and organics, condensing in the planet's shadow, while Saturn itself finished forming. Like Earth, Triton reigns. Like early Earth, it has rivers and seas, Only here they are made of liquid hydrocarbons, methane and ethane running in channels beneath an orange sky. Yet even amid this alien chemistry, the same cosmic geometry holds the direction of motion is inherited the structure familiar. From ring particles to moons, everything around Saturn keeps to its parent's turn, as if bound by a forgotten vow. The planet's rings are a frozen analogue of a moon-forming disk, a reminder of what once was and might yet become again. Some scientists believe new moons are still coalescing at the outer edge where gravity and collision continue their slow negotiation. The process that made Titan and its siblings has never truly ended. It merely operates at glacial tempo. Across the outer solar system, this pattern repeats with almost devotional precision. Uranus, despite its sideways fall, carries moons that orbit in the same plane as its tilted equator, meaning they too roll through space like a set of coins on their edge. Even after the planet's ancient trauma, the new moons were born aligned with the new reality, not the old. Neptune's regular moons, small and icy circle, counterclockwise and close to the equator, an unbroken continuation of order. And yet not every moon obeys. Some are captured wanderers, retrograde satellites like Neptune's Triton, a rogue that joined late and now circles backward. Triton's existence reminds us that harmony tolerates exceptions. The rule is resilient enough to include the irregular. But in the broad view, the message holds wherever a world has time and gravity enough to form a disk, the result is order, a smaller copy of the sun's lesson. The mechanics are universal. In fluid dynamics, a rotating body surrounded by gas will always drag that gas into co-rotation through viscosity and turbulence. The motion flattens into a disk as collisions erase vertical energy, just as in the solar nebula. Magnetohydrodynamic simulations from ESA and the Max Planck Institute show that circumplanetary disks obey the same equations as protoplanetary ones, scaled down by distance and mass, but identical in principle. Angular momentum is passed outward material inward until moons emerge as natural byproducts of balance. In essence, each gas giant is a solar system in miniature, and each moon a planet's child born remembering which way home lies. Emotionally, there is something tender in this repetition, a sense that the universe practices. Every planet, every moon, every disk is a rehearsal for the next scale of order. You can imagine Jupiter teaching its moons to move as it does, Saturn cradling Titan in its rings, Uranus rolling its moons along its tilted path, all of them echoing the sun's ancient spin. It's the same choreography, just smaller, quieter, closer to home. This is what coherence looks like when magnified across generations, motion nested within motion, each layer aware by gravity if not by mind of the one above it. The moons obey not because they must, but because the laws that made them leave no other graceful way to move. And so the solar system's harmony extends downward, fractal and faithful. From the sun's rotation to the planet's orbits, from the planet's spins to their moon's dances, the same counterclockwise inheritance unfolds like a spiral, repeating through smaller and smaller scales. What began as a single gesture in a collapsing cloud of gas has become a universe of orbits, within orbits all remembering the same direction, the same promise. A promise that even in chaos motion can still find order, and that every generation of worlds, no matter how small, still turns toward the same invisible rhythm. Next, we will lift our gaze outward once more to the farthest edges of the solar system, where this inherited order finally begins to fray, and motion starts to remember something older than the sun itself. Far beyond the bright warmth of the inner worlds lies a planet that moves through perpetual twilight, Neptune, the solar system's outer sentinel, and bound to it, circling the wrong way, is a moon that does not belong there. Its name is Triton, and it is both a prisoner and a relic, the moon that came from elsewhere. When Voyager 2 swept past Neptune in August 1989, it found something uncanny. The planet itself was unexpectedly alive, blue storms roaring across its atmosphere, high winds tearing faster than sound. But its largest moon was stranger still. Triton moved retrograde, orbiting opposite to Neptune's rotation, its path tilted and eccentric, its direction defying the inherited harmony of the solar family. In every regular moon system, satellites orbit the same way their planet spins, born from disks of gas and dust that remember that direction. Triton breaks that rule completely. The only way such a moon can exist is through capture. Billions of years ago, beyond Neptune stretched the Kuiper belt, a vast ring of icy bodies, orbiting the sun like debris left at the edge of creation. Among them were objects the size of small planets, frozen worlds of nitrogen and rock cousins of Pluto and Eris. Triton was one of these, an independent dwarf planet with its own companion travelling the Sun's path in peace. Then came the encounter, Neptune migrating outward during the early reshuffling of the solar system passed near Triton's orbit. For a moment, gravity hesitated between the two. If the encounter had been clean, Triton would have been flung away into interstellar space, but it wasn't. It came as part of a binary pair, two bodies orbiting one another. When Neptune's gravity seized the system, it tore the pair apart. One body was ejected to freedom, the other. Triton was captured, falling into Neptune's grasp like a dancer caught mid-step. Captured moons rarely last. Most are flung away or smashed. But Triton's orbit slowly tightened, circularized by tidal friction. Over millions of years, it became stable but retrograde, forever moving against Neptune's spin, the mark of its exile. Voyager 2's brief flyby revealed a world both young and ancient, familiar and alien. Its surface was smooth, strangely uncratered, patched with pinkish ice and dark streaks. The images showed frozen nitrogen plains ridged and veined like skin under pressure, and near the terminator where day met night, Voyager saw plumes. They were nitrogen geysers erupting up to 8 kilometers high, powered not by volcanism but by sunlight. The faint warmth of the distant sun penetrated a thin, translucent layer of frozen nitrogen, heating it just enough for vapor pressure to build. When the gas burst through the crust, it carried dark dust into the thin atmosphere, leaving long, wind-blown shadows across the ice. It was one of the most delicate forms of geology ever discovered, a world sculpted not by fire or flood, but by light itself at the edge of darkness. Triton's atmosphere is whisper-thin, mostly nitrogen, with traces of methane clinging to the surface, at just 14 microbars, less than 1/70th of Earth's pressure. Yet it changes with the seasons freezing and sublimating as Triton moves around Neptune every 6 days, completing one orbit for every rotation of its parent. Over its 165-year journey around the Sun, sunlight shifts between hemispheres, reawakening geysers and reshaping frost patterns. From infrared telescopes and more recently the James Webb Space Telescope, we've learned that Triton's surface reflects almost all light that touches it, the most reflective body in the solar system, even brighter than freshly fallen snow. Under that mirror lies a world of ices, nitrogen, carbon, monoxide water layered like a frozen ocean. There may even be liquid water buried deep below, warmed by tidal stresses as Triton's orbit continues to decay. And that decay tells the rest of the story. Because Triton moves backward around Neptune, tidal forces act differently on it than on regular moons. Instead of slowly pushing it outward as the Earth's moon drifts from us, Neptune's tides pull Triton inward, draining its orbital energy. The moon's path is shrinking imperceptibly each year, but steadily. In the far future, perhaps hundreds of millions of years from now, Triton will cross Neptune's roche, limit the distance within which a body can no longer hold itself together against tidal stress. When that moment comes, Neptune's gravity will rip Triton apart. The icy crust will shatter. Fragments will spread along the orbital path, forming a system of rings that may rival Saturn's in beauty. It will be a death that becomes creation, another pattern in the solar system's endless recycling of motion and memory. For a brief cosmic instant, Neptune will wear a crown forged from a captured world, before the fragments slowly drift and vanish into the cold. The irony of Triton is profound. A wanderer from the Kuiper belt, stolen from the sun's frontier, becomes the most loyal companion of Neptune, locked so tightly to its fate that it will one day die embracing it. Its retrograde motion, once rebellion, is now devotion. Its geysers, faint and temporary, are breaths of resistance against the deep freeze of time. Even in exile, Triton found rhythm, turning the wrong way, but still part of the same music. Voyager's departing image captured it perfectly, a half-lit crescent fading behind Neptune's blue arc sunlight, catching the edge of frost like a distant tear. The moon that came from elsewhere, still circling its captor, still whispering that, in a universe ruled by motion, even an outsider can find a place if only for a while. Next, we'll follow the story outward to where the sun's gravity fades, and the solar system's edge dissolves into interstellar dark. There, the inheritance of spin finally gives way to silence, and motion meets its cosmic frontier. They are the strays, the adoptees, the late arrivals, the refugees of gravity. Not born in the cradles of circumplanetary disks like the obedient regular moons, these small worlds were captured after the fact, folded into a planet's dominion, long after formation was supposed to be over. Their orbits tilted, stretched, and often backward carry the unedited history of encounters, breakups, and distant birthplaces. To study them is to open a file the solar system never meant to close. Among Saturn's far-flung attendants, Phoebe is the emblem of this story. It orbits retrograde far from the equator, on a path so inclined and eccentric that the geometry itself gives away its past. Phoebe didn't form beside Saturn, it came from elsewhere. When the Cassini spacecraft skimmed past in 2004, it found a world as dark as coal and scarred by a vast crater called Jason. Spectra revealed water ice and carbon-rich materials more akin to objects from the outer Kuiper belt than to Saturn's regular moons. Even stranger dust shed from Phoebe feeds a colossal tenuous Phoebe ring, a nearly invisible gauze discovered later in infrared, that wraps Saturn from 6 to over 10 million miles out. Some of that dust falls inward, painting the leading hemisphere of Iapetus jet black. A captured moon shedding a veil that repaints another history, literally settling out of sunlight. Where Saturn has a flagship refugee, Jupiter has a diaspora. The giant's outer realm is strewn with irregular moons, divided into clans with shared tilts and distances as though each group descended from a single shattered ancestor. The Himalaya group, named for its largest member, roughly 170 kilometers across circles, prograde but high above Jupiter's equator, their orbits elongated and restless. Their dull grey carbonaceous spectra point to captured asteroids rather than native children of a Jovian disk. Farther out, retrograde families like the Ananke and Calm groups move against Jupiter's spin, their orbital similarities implying a once larger body dismantled by collision or tidal stress. Each family is a chalk outline left by an ancient event, the breakup preserved not as rubble on a crater floor but as a constellation of orbits that still fits together. Irregular moons are almost always distant, inclined, and frequently retrograde because capture is difficult. A passing object must lose energy by atmospheric drag, by three-body interactions, or by breaking apart to settle into bond instead of flinging away. That difficulty is why their orbits look so precarious, high and lopsided, frozen at the edge of escape. In those shapes you can read the mechanics of their arrival. A prograde irregular like Himalaya hints at a gentle snare. A retrograde wanderer like Phoebe suggests a harsher, more abrupt encounter. What they preserve is not just kinematics, it's chemistry. Captured objects carry the fingerprints of the regions where they formed different ice ratios, darker organics, altered densities. When such bodies become moons, they ferry a sample of the outer solar system inward, and sometimes, like Phoebe's dust on Iapetus, they change the places they join. The irregulars are archives in motion, their orbits, the catalogue numbers. If capture moons reveal what a solar system keeps moon-forming disks, reveal how it begins. Around young giant planets, miniature versions of the protoplanetary disk, the circumplanetary disks collect gas and dust into the seeds of future regular moons. For years we inferred them from theory and shadow, now we can see them. Enter PDS-70, a young orange star about 370 light-years away, whose broad protoplanetary disk is famously carved by two embedded giant planets, PDS-70b and PDS-70c. The outer world, PDS-70c, has long been suspected of carrying a moon-forming disk. Radio images first hinted at it, then just STI with the sensitivity to weigh warm dust in the star's glare delivered a clearer view. In infrared, astronomers mapped thermal emission from a compact cool halo of material, co-rotating with the planet a circumplanetary disk a few lunar distances wide, on the order of an astronomical unit in diameter, plausibly massive enough to assemble multiple moons over time. Subtle brightness structure rings, and a dimmer gap suggests that even within this tiny disk, dust may already be shepherded by forming satellites, the first hints of a Galilean-like system in the making. The significance is hard to overstate. PDS-70c's disk is a scaled model of what once orbited Jupiter and Saturn, a compact flattened reservoir where regular moons condense in the same direction as their planet's rotation. JWST's infrared measurements paired with millimeter maps from ALMA bolster a picture that spans scales the same physics that flattens a stellar disk into planets, also flattens a planetary disk into moons. Collisions cancel vertical motion. Viscosity and magnetic coupling spread angular momentum. Accretion trickles inward while dust clumps grows and clears lanes. It is the cosmos performing the same choreography at a different tempo. Seen side by side, PDS-70's still forming moons, and the solar system's captured irregulars read like two chapters of one book. First comes birth in a disk-aligned circular prograde, where moons such as Io, Europa, Ganymede, Callisto, and Titan learn to orbit as their parent turned. Later, as the system stirs and migrates, come adoptions captured fragments like Phoebe, Himalaya, Ananke, Kami folded into service on awkward tilted paths. One process writes order, the other preserves accident. Together they make a moon system complete. There's a deeper poetry in this pairing. The regular moons are the smooth melody, recurrent, predictable, locked-in resonances that endure for eons. The irregular moons are the grace notes offbeat, surprising, sometimes discordant, reminding you that the score was once improvised. Remove either voice and you misunderstand the music. Without irregulars, we'd forget how violent the early choreography was. Without regulars, we'd never know it could relax into harmony at all. Think again of Phoebe's ring dust painting Iapetus of Himalaya's clan, tracing the silhouette of a lost progenitor. Think of JWST watching warm dust circle a newborn planet, the raw ingredients of someone else's Europa cooling in the dark. The lesson is as simple as it is. Beautiful capture events preserve history. Disk formation preserves habit. Both are memories, one of what should have happened, the other of what did. And because these refugees of gravity are small and numerous, their orbits are also laboratories for fragility. Solar tides, planetary resonances, and faint thermal forces, the gentle push of absorbed sunlight re-radiated at night can twist their paths over millions of years. Some will drift into families, some will collide and spawn fresh shards, some will eventually escape. Each slow change is a line added to the margin of the record. The archive keeps writing itself. In the end, the irregular moons teach humility. A planetary system is not just the grand pattern of disks and aligned orbits we like to diagram. It is also the roadside of lost stones that found new homes. If the regular satellites are a planet's children, the irregulars are its fosterlings, no less real, no less telling. They show us that order does not erase contingency, it absorbs it. And now, having traced adoption and birth around the giants, we can look outward to those bodies that don't orbit planets at all, but still refuse the main current, the asteroids and comets that move against the flow. Their rare backward paths and extreme tilts will extend this same lesson into the open lanes of the sun, where refugees of a different kind keep their own uneasy stability. Not all rebellion belongs to the planets and moons. Some comes from smaller, humbler travelers' rocks that forgot which way the solar system turns. Among the billions of asteroids that circle the sun, nearly all flow with the same counterclockwise tide, but a few, like salmon in a cosmic river, swim against the current. They are the retrograde asteroids, and their existence is one of the strangest surprises of modern celestial mechanics. In 2018, astronomers at the University of Hawaii and Canada-France-Hawaii telescope announced a discovery that shook the assumption of uniform motion. A small, faint body designated 2015 BZ509, or Kaiapauka Awela, the mischievous one in Hawaiian, was found orbiting the Sun in reverse, sharing nearly the same average distance as Jupiter, yet moving opposite to every major planet. Imagine the scene: Jupiter, a massive world of gas thundering eastward along its orbit, and a single pebble-sized asteroid threading the same track in the opposite direction, passing head-on every 12 years at relative speeds over 100,000 kilometers per hour, and somehow surviving. How the answer lies in resonance and the art of celestial choreography. Kaiapauka Awela is caught in what astronomers call a retrograde 1-1 resonance with Jupiter. That means it takes exactly as long to orbit the Sun as Jupiter does, but it travels in the opposite direction. Each time they pass, gravitational timing ensures that the asteroid always meets Jupiter at the same point in space, moving too fast to be captured, but too perfectly phased to be destroyed. It's a cosmic handshake performed at sword's length, gravity and momentum in perfect negotiation. Numerical simulations show that this arrangement has been stable for billions of years. That longevity implies one of two origins. Either the asteroid formed in the early solar system and was flipped by gravitational scattering among the giant planets, or it came from outside the solar system entirely, an interstellar wanderer trapped by Jupiter's pull. To understand the first scenario, imagine the early Sun surrounded by chaos. Jupiter and Saturn migrating, flinging planetesimals in all directions. Some were ejected forever into interstellar space. Others were tossed into high-inclination orbits, spinning around the Sun like sparks from a forge. Through repeated gravitational kicks, a few had their orbital planes twisted past 90, turning them into retrograde survivors. Most of these misaligned bodies were lost over time, but the rare ones that found resonant sanctuaries with the giant planets could persist. Caopaiocca may be the last of its kind, a relic of that wild reshuffling, preserved by the very planet that once threatened to destroy it. The alternative is even more dramatic: interstellar capture. Computer models show that a wandering object from another star system, if it enters the solar system at just the right speed and angle during Jupiter's migration, can be caught into a stable retrograde orbit. If that is true, then 2015 BZ509 might be an immigrant, a visitor from a different sun now naturalized into our cosmic citizenship. Its chemical composition, still unknown, could carry fingerprints of an alien nursery. The first confirmed interstellar asteroid Oumuamua passed through in 2017 and escaped. Caopaiocca may be one that never left. Retrograde asteroids are not unique to Jupiter's neighborhood. Others have been found near Saturn, Neptune, and even among near-Earth asteroids. Some follow comet-like paths with inclinations above 100 degrees, looping backward through the inner system before being flung out again. Their orbits are maps of the solar system's forgotten turbulence, records of gravitational arguments that never fully settled. Each represents a kind of controlled chaos motion that defies the flow but still honors the law. That paradox is what makes them so mesmerizing. They are not rebels in defiance of gravity, they are rebels through gravity. They exist because order itself creates niches where disorder can endure. Resonances, the same mathematical structures that stabilize regular moons and planets, also provide safe harbors for misfits. The solar system's architecture is flexible enough to allow contrarians a home. In this, the cosmos mirrors its own philosophy. The universe doesn't punish anomaly, it integrates it. A retrograde asteroid properly timed is as eternal as any prograde planet. The rules are symmetric, and symmetry means freedom. If motion clockwise is allowed, then so is motion counterclockwise, provided energy and geometry align. Order then is not the absence of rebellion, it is the container that makes rebellion possible. The counter-spinning asteroids are its proof. They trace invisible figure eights through a system that long ago learned to welcome outliers to hold diversity without collapse. To watch their paths plotted in simulation is to see a solar system alive with countercurrents like eddies in a vast sea. Most flow smoothly with the tide, a few curl back, glinting briefly against the stream, before vanishing into the deep. If you could stand somewhere above the sun's north pole and speed up time, you'd see those rare backward orbits like silver threads winding through a golden spiral, a subtle reminder that even in cosmic mechanics, individuality survives. The next movement in this story carries us to the frontier, where the sun's dominion fades, where even the backward dancers become indistinguishable from the interstellar drift. Beyond that line lie the long-period comets and the invisible swarm of the Oort cloud bodies so distant they barely remember which way they were meant to move. They are the final archive of motion itself, the boundary where the solar system's order dissolves into the freedom of the stars. From a distance, the solar system looks serene, planets tracing smooth ellipses, moons, circling faithfully, everything obeying an invisible rhythm. But beneath that calm lies something wilder, chaos, mathematical, precise, and paradoxically stable. The most striking proof of this hidden balance is the way that retrograde asteroids, those tiny bodies, moving backward through the planetary lanes, manage to coexist with billions of prograde travelers for millions of years without catastrophe. In classical terms, this should not be possible. A retrograde asteroid shares the same space as planets and other asteroids, but moves in the opposite direction. Every near encounter occurs at dizzying relative speeds, sometimes exceeding 120,000 kilometers per hour. One would expect constant collisions or quick ejections, yet some of these backward drifters have persisted since the birth of the solar system. Their survival is not an accident, it's the geometry of chaos doing what order alone could not. The key lies in resonance and phase protection, a dance of timing so intricate that chance itself seems orchestrated. Each retrograde object occupies a precise orbital resonance with a planet. In those configurations, gravitational tugs that might normally accumulate into disaster instead cancel out. When one encounter speeds the asteroid up, the next slows it down. The orbit oscillates chaotic in detail, but bounded overall. The asteroid never strikes because the pattern repeats with irregular perfection. Take 2015 BZ509, Caopaiocca, the poster child of this phenomenon. Its retrograde 1-1 resonance with Jupiter, discovered through decades of sky surveys, keeps it eternally just out of harm's way. Whenever Jupiter approaches, Kayapauka Awela happens to be on the opposite side of the Sun. After each near pass, the gravitational energy exchange shifts its orbit slightly, but in a way that preserves the overall relationship. In phase space diagrams, its path is not a simple circle, but a twisting torus, a mathematical donut of possibilities, chaotic in the short term, self-contained in the long term. It's as if Jupiter and the asteroid are partners in a cosmic fencing match, each lunge and parry unpredictable, yet the duel itself never ends. This counterintuitive stability has been confirmed across the solar system. Using the Neowise infrared telescope, astronomers have catalogued dozens of high-inclination and retrograde objects whose orbits persist through delicate resonance webs with Jupiter, Saturn, and Neptune. The data reveal that these bodies tend to cluster in regions where gravitational interactions create overlapping resonances zones that paradoxically are both chaotic and confining. Within these dynamical traps, small perturbations don't eject an asteroid. They keep it wandering within invisible boundaries like a moth trapped in a storm of light. The Gaia mission, with its precise stellar and asteroid measurements, has refined this view even further. Gaia's astrometry has mapped the motions of hundreds of thousands of small bodies to micro-arcs a second accuracy, showing that chaos does not mean randomness, it means bounded unpredictability. Some orbits diffuse slowly through phase space, their inclinations and eccentricities meandering like drifting smoke. Others hover around equilibrium points for eons before switching states. The outcome of any single orbit may be uncertain, but the population behavior is statistically stable. The solar system viewed as a whole is a vast chaotic attractor that keeps everything moving but rarely breaks. In physics, this paradox is captured in the language of non-linear dynamics. Systems with many interacting bodies like the Sun and its planets exhibit sensitive dependence on initial conditions. Tiny differences can produce huge divergences over time. But rather than dissolving into disorder, such systems often settle into strange attractors, regions of stability wrapped in chaos. A retrograde asteroid's orbit might wander unpredictably on human timescales, yet remain confined for billions of years because energy exchanges oscillate around that attractor. The chaos itself becomes the mechanism of preservation. It's as though the solar system, instead of resisting disorder, uses it as a shock absorber. Each unpredictable encounter dissipates potential instability, preventing precise resonances from locking too tightly. Perfect order is brittle. Chaotic motion is flexible. That flexibility is why retrograde asteroids can cross planetary orbits thousands of times and never collide. In this view, the solar system is not a flawless clock, but a breathing organism sustained by the constant give and take of gravity's chaos. Its harmony is statistical, not absolute. You can predict its music, but not its notes. Neowise and Gaia's discoveries make that explicit. The long-term survival of retrograde asteroids proves that the system's equilibrium is dynamic, not static stability achieved through perpetual motion. If you could visualize the inner solar system sped up 1 billion times, you'd see these tiny bodies as silver sparks weaving through the prograde flow, sometimes plunging inward toward Mars or Earth, sometimes retreating past Jupiter's gates. Their paths would look like tangled threads crossing and recrossing, never the same twice, and yet the tapestry itself would remain whole. That is the secret of chaotic stability. It's not about controlling motion, but allowing freedom within bounds. The system's integrity depends on its ability to accommodate imperfection, to let disorder act as a buffer rather than a flaw. And perhaps in that lesson, the cosmos offers its quiet philosophy. A structure that never flexes will shatter. A system that tolerates uncertainty can last forever. Even the wildest orbits running against the tide become part of the pattern when chaos itself learns how to keep the rhythm. Next, we travel to the solar system's fading edge, the distant sphere where even chaos thins, where gravity becomes memory and the sun's order dissolves into starlight, the Oort cloud, the final frontier of motion. They appear without warning, faint smudges at the edge of telescopes, then flaring into long radiant tails that seem to defy gravity itself. The ancients saw them as omens of disaster. Astronomers now see them as messengers, time capsules, from the very dawn of the solar system. They come from the frozen outskirts, the Kuiper belt and the Oort cloud, drifting for millions of years in darkness, before plunging inward toward the sun in a single incandescent act. They are the comets, and each one is both an archive and a performance: ice meeting fire, silence meeting light. Every comet's journey begins far beyond the planets, in a region where the sun's warmth is just a rumour. Two main reservoirs hold these frozen wanderers: the Kuiper Belt, a flattened ring beyond Neptune houses; short-period comets, those that return every few decades or centuries. The Oort cloud, a vast spherical shell extending up to a light-year away, is home to the long-period comets that might visit only once in the lifetime of civilization, if ever. Both are remnants of the same ancient nebula that formed the planets scattered outward billions of years ago by the gravitational slingshots of Jupiter and Saturn. In those early days, as the giant planets migrated, they hurled trillions of icy bodies into exile. Some settled into the Kuiper Belt's thin plain, others were ejected so far that the sun's pull grew weak and diffuse. Together they formed the solar system's memory sphere, a halo of potential motion waiting to be reawakened. Sometimes a passing star or the slow tug of the Milky Way's tide disturbs one of those frozen relics. It begins its long fall inward, accelerating for millions of years until sunlight strikes its surface. The ice sublimates, turns directly to vapor, and jets of gas and dust burst outward, sculpting the glowing tail that stretches for millions of kilometers. That tail always points away from the sun, a banner of heat and momentum, not direction of travel. It is the breath of a world that has slept since creation. These comets trace every possible inclination. Some glide gently along the planetary plane, others dive steeply from the poles, or even sweep backward, moving retrograde through the inner solar system, like ghosts from a forgotten era. They do not respect the ecliptic's order because they come from a place where there is no order, where the solar system dissolves into galactic space. Every appearance is an intrusion of the infinite. Among the countless comets, two have engraved their names into human memory: Halley and Hale-Bopp. Each represents one half of this cosmic duality: short and long, tame and wild, known and eternal. Halley's comet, the most famous of all, is a short-period traveller returning roughly every 76 years. It last visited in 1986, a dim apparition caught by spacecraft in the glare of its own dust. Yet for millennia before that, it was the omen that bound generations. Chinese astronomers recorded it in 240 BCE. Medieval monks drew its starburst in the Bayeux Tapestry. It is the one comet whose orbit we remember the bridge between myth and mechanics. But even Halley carries rebellion in its motion. It moves retrograde, orbiting the sun backward at a steep inclination of 162 degrees. A messenger from the outer dark captured long ago by Jupiter's gravity, it chose to keep its old direction, as if the cosmos allowed it to retain its accent. Every passage through the inner solar system sheds more of its body into space, and someday Halley will vanish. Dust returned to the current from which it came. Yet while it lasts, it reminds us that not all motion must conform. Even the brightest wonders can go their own way and still belong to the same system. Hale-Bopp, by contrast, is a child of distance, a long-period comet from the Oort cloud. Discovered independently in 1995 by Alan Hale and Thomas Bopp, it was visible to the naked eye for 18 months, one of the most spectacular comets of the 20th century. Its orbit stretches over 250 astronomical units, nearly 40 billion kilometers, taking it far beyond Pluto before returning. It won't be back for another 2,500 years. Hale-Bopp's nucleus is enormous, about 60 kilometers across, and so active that even in the cold of the outer solar system it was already venting gas. When it neared perihelion in 1997, its twin tails, one blue with ionized gas, one golden with dust, spanned tens of millions of kilometers, visible even under city lights. For those months it became a moving cathedral, a reminder that our star is only one stop on a grander galactic road. Modern missions have turned comets from omens into laboratories. In 2014, the European Space Agency's Rosetta spacecraft landed its probe Philae on comet 67P Churyumov-Gerasimenko. The images it returned showed cliffs of black ice jets of gas bursting from fissures and organic molecules, the raw precursors of life. Comets once feared as destroyers are now seen as deliverers, perhaps the couriers that brought water and carbon chemistry to the young Earth. Each retrograde pass through the inner solar system is not just a spectacle, but a reenactment of that first gift. NEOWISE's recent surveys have expanded this narrative further. Infrared data from the WISE spacecraft revealed that short-period comets from the Kuiper Belt often have lower albedo, darker surfaces than long-period Oort cloud comets, suggesting different evolutionary histories. As they repeatedly graze the sun, their volatile ices bake away, leaving inert crusts that dull their shine. The newcomers from the Oort cloud, by contrast, blaze brilliantly on their first descent, virgin ice meeting sunlight for the first time in 4 billion years. Every retrograde path, every high inclination swing is a signature of the system's youth and violence. Comets travel on these impossible orbits because they were thrown there by giants sculpted by encounters with Jupiter and Saturn during the Great Planetary Migration. Their current eccentricities are fossils of gravitational mayhem now frozen into beauty. To watch a comet is to witness time itself curve. You see matter that predates Earth's mountains and oceans, ignited briefly by the same sun that has burned since the beginning. When it fades, it returns to invisibility outward again, into the slow cold halo of the Oort cloud until another disturbance awakens it in another age. Somewhere out there, millions more wait. They are the solar system's drifting memory, the messengers of ice and fire carrying news between the edge of interstellar space and the heart of our small star's domain. And as they pass, they whisper a quiet lesson, written in their tales that even at the boundaries of order, chaos can still shimmer, with purpose and motion, no matter how wild, always finds its way home. At the farthest edge of the sun's dominion lies a realm so faint it cannot be seen, only inferred, a frozen frontier, where sunlight is as weak as starlight and time moves differently. This is the Oort cloud, the solar system's outermost memory, a spherical veil of ice and stone stretching perhaps 1 light year in every direction. It is not a place so much as a boundary, a region where the sun's gravity fades into the collective pull of the galaxy. Everything beyond is interstellar, everything within still belongs just barely to us. To imagine the Oort cloud picture, billions, maybe trillions of icy bodies, each no larger than a mountain orbiting so far from the sun that a single circuit could take millions of years. They form a diffuse halo around the planets, a cosmic dandelion of frozen seeds. Astronomers believe it began around 4.6 billion years ago during the solar system's violent adolescence. When Jupiter and Saturn migrated through the primordial disk, their gravity became a catapult, flinging countless planetesimals outward. Most were lost to the void forever, but some slowed enough that the sun retained a faint hold on them. Over eons, the distant tug of the Milky Way's own mass, what scientists call galactic tides, rounded their orbits into a sphere. What had been a flat ring like the Kuiper Belt became a shell of wandering ice, a blurred horizon between solar order and galactic chaos. The Oort cloud is so vast that its inner edge might begin near 2,000 astronomical units, while its outer rim could reach 100,000 AU, 1,000 times farther than Pluto. Within that expanse, the sun's light is almost meaningless, less than a candle seen from across an ocean. Temperature hovers around 270 Durham, just above absolute zero. The comets there sleep locked in darkness until something disturbs them. Sometimes that disturbance is a passing star. In 2015, astronomers using data from Gaia identified a red dwarf binary called Schultz's star that brushed past our system 70,000 years ago, within just 8 light-years, close enough to perturb the outer Oort cloud. It may have sent a slow cascade of comets inward, some of which might only now be approaching the sun. Each stellar encounter stirs the cloud like wind through deep snow, sending faint avalanches toward the inner worlds. At other times, the trigger is subtler, the rhythmic gravitational heave of the Milky Way itself. As the solar system drifts through the galaxy's spiral arms, galactic tides flex the Oort cloud, alternately squeezing and stretching it. These tides act like the oceanic pull of the moon on Earth, gentle but relentless. Every few tens of millions of years, they loosen a few icy grains from the outer shell, nudging them sunward. Those returning fragments become the long-period comets' bodies whose orbits stretch so wide that they may appear only once in all of human history. When they approach the inner solar system, sunlight wakes them, and they begin to speak in vapor and light. The gases they release are older than any rock on Earth, older even than the planets themselves. They are the unaltered chemicals of the primordial nebula. Thanks to the James Webb Space Telescope, scientists can now listen more closely to that whisper. In 2023, JWST trained its infrared instruments on several active comets, among them Comet 238P Reid and Comet 67P Churyumov-Gerasimenko, and detected unmistakable signatures of carbon dioxide, CO2, methane, and complex organic molecules. These are the same compounds found in meteorites and interstellar clouds, the essential ingredients of prebiotic chemistry. Webb's spectra also revealed faint traces of crystalline silicates, proof that material from the warm inner solar system was once transported outward, frozen, and stored in the Oort cloud's deep freezer. That means every long-period comet returning to the Sun carries both inner and outer stories molecules forged near the newborn Sun and ices condensed in the galactic dusk. Each is a message in a bottle tossed billions of years ago, finally drifting back into the light. If we could stand on one of those icy worlds before it wakes, the sky would be almost pure black. The Sun would appear no brighter than any other star. Around us would stretch an ocean of frozen silence, ancient ices dusted with cosmic rays, fractured by micrometeoroid scars yet still pristine. Beneath that surface lies chemistry unchanged since the age when hydrogen first mingled with carbon and oxygen to form the first water molecules. It is the memory of formation itself preserved by distance. When such a body finally turns inward, gravity writes poetry with fire. The Sun ignites its coma, the tail unfurls, and the message is released not in words, but in spectrum lines of carbon oxygens, nitrogen whispering through the dark. To astronomers, each line is a syllable of the solar system's autobiography. To dreamers, it is a letter from the past, a reminder that even the coldest things can shine when they fall homeward. The Oort cloud will never be seen directly. It's too vast, too faint, too far. Yet we know it's there because its messengers keep arriving slowly, unpredictably, beautifully. Every comet we witness is a returning thought from that frozen frontier, a fragment of the Sun's forgotten youth. They whisper as they burn, "Remember me." I was there when the universe was still learning how to hold light, and as they vanish back into the dark, they leave us with a quiet truth that even at the edge of emptiness, the universe keeps its memories safe in ice, waiting for the warmth of curiosity to melt them again. They arrive blazing, but they are not flames. They are returns, memories rekindled. Every comet that sweeps through the inner solar system is a traveller from the deep past, and for a few luminous weeks we can touch it with instruments, even with our machines. 2 missions, Deep Impact and Rosetta, did more than photograph these ancient visitors. They touched their hearts, and in doing so turned myth into data, and data into wonder. In July 2005, NASA's Deep Impact sent a copper projectile into Comet Tempel 1, slamming into it at 10.2 kilometers per second. For a moment, the void bloomed an eruption of ice dust and vapor that revealed what a comet truly is: not a solid ball of rock, but a fragile agglomeration as porous as fresh snow and blacker than coal. The impact exposed subsurface ices that had been sealed since the solar system's birth, crystalline water, carbon monoxide, methanol, and traces of organic molecules. The instruments aboard the flyby craft caught spectral signatures of amino acid precursors, simple hydrocarbons and silicates laced with carbon chemical relics from before Earth itself had a crust. Deep Impact proved what astronomers had long suspected. Comets are not dirty snowballs, as Fred Whipple once described, but snowy dirt balls, complex bodies of dust and ice, layered, fragile, and chemically rich. Each one is a frozen chemistry set that remembers the first seconds of planetary construction. Its interior is riddled with voids, its density less than half that of water. Strike it, and it doesn't shatter it. Sighs releasing ancient breath. 9 years later, in 2014, another mission descended far more gently. The European Space Agency's Rosetta spacecraft became the first to orbit a comet, and its lander Philae the first to touch one. Its target, Comet 60th P Churyumov-Gerasimenko, a strangely shaped world of twin lobes joined by a narrow neck like 2 mountains frozen in an embrace. From orbit, Rosetta's cameras revealed cliffs hundreds of meters high, fields of pebbles, and geysers of vapor jetting into space as the comet warmed. Its surface temperature hovered near 200 degrees, yet sunlight was enough to wake the ice beneath. Philae's short-lived instruments measured the mechanical softness of the soil powder atop compact dust and sniffed a cocktail of volatile gases, carbon dioxide, formaldehyde, ammonia, hydrogen, cyanide, sulfur compounds, and the faint spectral whisper of amino acids, including glycine. That single molecule glycine was the key. It is one of the building blocks of life, an amino acid found in every living cell on Earth. And here it was, adrift in the coma of a comet forming naturally in the chemistry of space. Rosetta confirmed that comets are chemical archives of the early solar system, but also chemical laboratories still running their experiments. The proportions of heavy hydrogen, deuterium in cometary water differ from Earth's oceans, implying that comets were not the only source of Earth's water, yet they may have contributed key organic compounds. Other missions and meteorite analyses have expanded this idea. Carbonaceous chondrites, the rocky cousins of comets, contain sugars, nucleobases, and even lipids. Together, these findings suggest that the precursors of life were widespread long before life itself appeared. Here lies one of the great scientific poems of our age, the hypothesis of panspermia. It does not claim that life itself traveled between worlds, but that its ingredients did. Complex molecules, amino acids, hydrocarbons, perhaps even fragile strands of RNA-like precursors may have formed in the cold chemistry of interstellar dust, condensed into comets, and been delivered to young planets on fiery trajectories. Each impact would have scattered organic compounds across new worlds, seeding potential wherever conditions allowed. It is life not as a miracle, but as a statistical inevitability of chemistry and motion. The physics of comets makes them ideal couriers. They spend billions of years preserved in deep freeze at the solar system's edge, shielded from radiation by their own dust. When disturbed, they plunge inward retrograde or prograde, it doesn't matter. And, as they near the sun, sublimation sprays their stored chemistry across the vacuum. Every tail is a trail of molecular confetti drifting through the inner solar system, settling on planetary atmospheres even on Earth. In that sense, the seeds of life ride backward orbits, falling against the grain of planetary order as though defiance itself were fertile. Spectra from Rosetta, NEOWISE and JWST now confirm this cosmic distribution network. Webb's mid-infrared detectors have observed complex organics, including ethane, methanol, acetone and formaldehyde streaming, from comets as far out as Jupiter's orbit. These are not isolated compounds, they are the alphabet of biochemistry written across ice and dust in every direction the solar wind can carry it. Some of those molecules eventually find planetary surfaces. Some burn in atmospheres, forming simple amino acids and new in lightning or impact fireballs. Life, it seems, is less a local event than a continuum of chemistry, persistent wandering, waiting. Seen this way, every comet becomes more than a frozen relic. It is a messenger, part archivist, part missionary. It remembers what the solar system once was, and it distributes what it could yet become. Its backward orbit is not rebellion. It is return, a spiral of matter, memory and possibility. When we watch a comet streak across the night sky, we're not merely witnessing ice evaporate. We are watching history ignite, releasing the molecules that may have started the story of us. And as its tail fades back into darkness, the lesson remains glowing in the sky. Life does not stand still. It travels, burns, reforms, and carries its spark forward through time, on paths both with and against the current. The universe is not a cradle of life. It is a carrier, and comets are its couriers forever falling home. They come from beyond our map, silent, unclaimed, carrying the handwriting of another star. For centuries we thought comets were ours alone, children of the sun returning after long exiles. Then in the span of just 2 years we saw two that broke the rule, Oumuamua in 2017 and Tui-Borisov in 2019. Neither belonged to our solar system. They were interstellar visitors, the first physical proof that the space between stars is not empty at all, but threaded with travelers' messengers of a connected cosmos. The first arrived quietly. In October 2017, the Pan-STARRS telescope in Hawaii caught a strange point of light speeding through the inner solar system, on a path too steep to have come from any known orbit. Calculations showed it was hyperbolic. Its velocity, even after losing energy to the sun's gravity, was high enough to escape forever. This object, later named Oumuamua, meaning a messenger from afar, arriving first, had come from the direction of Lyra, and would never return. Yet its behavior was a riddle. It had no visible coma, no tail, and reflected light like metal or rock. Its brightness varied wildly, as if it were tumbling end over end, perhaps an elongated shard, 100 meters long, thin as a skyscraper's floor plate. As it passed, it accelerated slightly in a way consistent with outgassing, but without the expected visible jets. Some called it a comet without ice, others an asteroid that had lost its volatiles, or even a fragment of something engineered. But regardless of its nature, one truth remained: it was the first known object ever observed to come from another star and cut through the solar system. A visitor older than our sun itself, its orbit linking two distant stellar neighborhoods for a fleeting moment. 2 years later, another interstellar traveler confirmed what Oumuamua hinted. Tui Borisov, discovered by amateur astronomer Gennady Borisov in Crimea, displayed the unmistakable tail of a true comet, a nucleus wrapped in gas and dust venting carbon monoxide and cyanide. Unlike Oumuamua, it behaved exactly as theory predicted, yet its composition was alien. Spectroscopic data from ALMA and the Hubble Space Telescope revealed unusually high levels of carbon monoxide, far more than typical solar system comets. This implied it had formed in an environment colder than our Kuiper belt, perhaps around a dim red dwarf star, where temperatures remained low enough for CO to freeze solid. As Borisov crossed the inner solar system, its coma expanded to tens of thousands of kilometers, glittering faintly against the stars. Then it began to fragment, dispersing into dust. As it receded, its brief visit ending in self-dissolution. For the first time in human history, we had direct evidence that material forged in another planetary system could wander into ours. The solar system was not an island. It was a node in a galactic network of debris and exchange. Astrophysicists now suspect that such encounters are not rare at all, only rarely observed. Simulations suggest that every star system ejects trillions of comets and planetesimals. During formation, their chaotic gravitational interactions, flinging small bodies outward at escape velocity. Over billions of years, those frozen fragments drift between stars like seeds in a cosmic wind. The Sun itself may have expelled countless icy bodies that now travel through the galaxy, some perhaps destined to be captured by other stars in turn. If one interstellar comet could reach us within a few years of observation, then the galaxy must be teeming with them. Between the spiral arms of the Milky Way, a thin dust of frozen wanderers circulates, carrying the signatures of every kind of chemistry: water, ammonia, organics, and metallic minerals waiting for gravitational ports of call. Each pass, each capture, each grazing flyby mixes the materials of different suns, subtly blending the galactic ecosystem. Viewed this way, the Oort cloud is not merely the Sun's shell, it is also the front line of interstellar traffic. Every few million years, as the Sun drifts through dense star fields or molecular clouds, other systems' comets pass close enough to be caught. The boundary between ours and theirs is porous. Our long-period comets may include immigrants whose home stars have long since moved on, carried away by the slow rotation of the galaxy. Some astronomers even suggest that Oumuamua and Borisov were once members of a distant Oort clouds, set adrift when their parent stars brushed too close and scattered their outer debris. The galaxy in this view is a giant comet exchange recycling material, through slow encounters maintaining a chemical continuity that spans light years. And here the story turns philosophical. If stars can trade comets tiny frozen fragments of their birthplaces, what else might they trade? The gravitational rules are the same for all scales. A passing star could, under rare but possible conditions, capture a rogue planet the way Jupiter captures comets. Indeed, astronomers have already detected free-floating planets, unbound to any star wandering the galactic dark. Some were likely expelled from their native systems during chaotic youth. Others may drift close enough to be adopted by a new sun someday. The logic is hauntingly simple. If comets can connect star systems chemically, then planets could connect them gravitationally. Perhaps the very idea of our solar system is temporary, its boundaries written in orbital agreements that time will eventually renegotiate. What we see as isolation may only be a pause between exchanges, and so as Oumuamua recedes into interstellar night and Borisov's dust fades, the thought remains: the cosmos is not a set of separate stars but a continuum of motion. Material flows across its vast distances as naturally as rivers through a delta. Comets are the couriers of that flow, proof that no world stands completely alone. The next question rises like dawn over that idea, bright and unsettling. If stars can trade comets, these icy messengers of chemistry and memory, could they also exchange worlds? Could planets too wander from one sun to another, carrying not just molecules, but oceans, atmospheres, perhaps even life? That is the story waiting beyond the next horizon, the tale of the interstellar orphans and how the galaxy itself may one day learn to share them. The year was 2009, and astronomers thought they already understood how planetary systems behaved. Planets formed in disks spun in one direction. Therefore, all planets should orbit their stars the same way their stars rotate, orderly, aligned, obedient. Then came WASP-17b, and that simple picture shattered. It was the first confirmed planet ever seen orbiting backward-moving retrograde around its star, an entire world defying the spin of its own sun. The discovery began with the Wide-Angle Search for Planets WASP project, a network of robotic cameras scanning millions of stars for the telltale dimming of transits. In 2009, data from a bright F-type star in the constellation Scorpius, catalogued as WASP-17, showed a giant planet crossing its face every 3.7 days. That alone was not unusual. Dozens of hot Jupiters were already known. What made this one extraordinary was how its orbit compared to the star's rotation. By using high-resolution spectroscopy, astronomers detected a strange reversal in the way the star's light shifted during transit, proof that the planet was moving the wrong way. This effect is known as the Rossiter-McLaughlin effect, a subtle but powerful test of cosmic choreography. As a planet passes in front of its star, it blocks part of the rotating stellar surface. If the planet first covers the side rotating toward us, the star's apparent radial velocity shifts slightly redward. If it covers the side rotating away, the shift goes blue. By tracking this minute spectral dance, scientists can tell whether a planet's orbit aligns or conflicts with the star's spin. For WASP-17b, the shift was reversed, an unmistakable signature of a retrograde orbit tilted by roughly 150 degrees relative to the star's equator. It was the first time humanity had caught a planet circling against the grain of its sun. How could such a world exist? The answer lies in the violent adolescence of planetary systems. Gas giants like Jupiter form far from their stars where ice can condense and massive cores can grow. To end up skimming the star's atmosphere as WASP-17b does, they must migrate inward, a process driven by gravitational interactions. Some drift gently through the gas disk, others suffer brutal encounters. A close brush with another giant planet or a passing companion star can tilt or even flip the orbit, sending the planet spiraling inward on a retrograde path. Tidal forces then circularize the orbit over millions of years, locking the planet into a tight embrace with its star. WASP-17b now orbits so close that its year lasts less than 4 Earth days. It is tidally locked, showing one hemisphere in perpetual daylight and the other in endless night. The day side burns at nearly 500 degrees Celsius, hot enough to vaporize clouds and sculpt vast atmospheric flows. The night side, plunged into shadow, radiates heat back into space, producing violent winds that whip around the terminator line at thousands of kilometers per hour. It is a world of ceaseless motion, a backwards windmill in the furnace of its star. For years, its strangeness was known only through indirect light curves. Then in 2023, the James Webb Space Telescope turned its infrared eye toward WASP-17b, and what it found rewrote the story yet again. Using its mid-infrared instrument MIRI and near-infrared spectrograph, NVR-SPEC, Webb captured the most detailed transmission spectrum ever recorded for a retrograde exoplanet. Across wavelengths from 5 to 12 microns, it detected clear absorption features of water vapor, sodium, and most strikingly crystalline quartz, nanograins suspended in its atmosphere. These were the first direct signs of silicate clouds ever observed outside the solar system. The quartz grains, only a few hundred nanometers across, reflect infrared light in a distinctive way, producing spectral shoulders that match theoretical predictions. In WASP-17b's blazing sky rock literally rains as glass dust and mineral storms swirling backward around a rebellious world. Webb's data also refined the planet's radius and density. At nearly twice Jupiter's size but less than half its mass, WASP-17b is one of the largest and puffiest planets known. Its gravity barely holds its atmosphere. Solar winds strip material into a faint trailing envelope, perhaps forming a comet-like tail. The low density suggests deep internal heating, tidal flexing, as the planet's orbit tries to synchronize with the star's pull, a perpetual struggle between alignment and defiance. In that struggle lies the deeper meaning of WASP-17b's discovery. For billions of years, it has circled backward yet stable proof that cosmic order can include contradiction. Its existence forced astronomers to abandon the tidy vision of solar systems as perfectly aligned miniatures of our own. We now know that chaotic migration, gravitational scattering, and stellar tides sculpt far stranger architectures than we imagined. Half of all known hot Jupiters are now suspected to have significant orbital tilts, and a few others like HAT P7b and Kepler 63b may also be retrograde. What once seemed an anomaly has become a window into the true diversity of planetary motion. So what does it mean, this planet that spins against its sun? It is more than a curiosity, it is a symbol of survival through turbulence. WASP-17b began as an exile hurled inward by violence, yet found a lasting orbit amid the flames. Its atmosphere glitters with vaporized minerals, its winds roar backward through light older than Earth's continents, and still it endures, moving opposite to everything around it. In its strange reversal lies a universal truth motion, remembers its origins even when the direction changes. Like a comet returning from the dark or a thought looping back through time, WASP-17b reminds us that the cosmos keeps both order and rebellion in the same breath. And if a planet can defy its sun and survive, what else out there might defy the gravity of its birth and live on? At first, astronomers imagined that every solar system would look like ours, planets, orbiting neatly along a single plane, all spinning in the same direction, all aligned with their parent star like obedient dancers circling a candle. But as the exoplanet revolution unfolded, that illusion dissolved. With every new discovery, order looked less like the rule and more like the exception. The cosmos, it turned out, prefers eccentric choreography, tilted, twisted, and sometimes upside down, and nowhere is that clearer than in the strange statistics of exoplanets. In the years after WASP-17b revealed that orbits could run backward, astronomers began measuring the spin-orbit alignment of other hot Jupiters, using the same method, the Rossiter-McLaughlin effect. The pattern that emerged was astonishing. The sky was full of rebels. One of the first and most striking was HAT P7b, a bloated gas giant, 1,000 light-years away in Cygnus. It whirls around its star every 2 days on a steeply tilted, possibly retrograde path. When NASA's Kepler telescope watched it, the planet's orbit caused predictable brightening and dimming, but with a twist, the star itself pulsed in response. Tidal stresses from the misaligned orbit set off oscillations inside the star, literal waves of stellar sound echoing every time the planet passed. The planet was effectively playing its star like an instrument. Then came Kepler-17b, another inflated giant, but one locked in an intricate gravitational ballet. Its orbit is slightly tilted, yet not chaotic. It synchronizes with the star's magnetic cycles, creating rhythmic brightness variations, as if the planet and the star were whispering in code. Each orbit pulls on star spots, subtly dragging them across the stellar surface. Where the Sun and Earth form a quiet duet, Kepler-17b and its star perform a turbulent jazz piece, forever improvising in magnetic time. And at the far edge of the scale sits Kelt 9b, a planet so extreme it seems to mock the term hot Jupiter. Orbiting an A-type star over 10,000 Kelvin, it circles once every 1.5 days in a plane tipped nearly sideways. Daytime temperatures reach 4,300 Celsius, hot enough to vaporize iron, titanium, and magnesium. Astronomers using Hubble and Cheops have found a thin veil of metallic vapor escaping the planet, entirely streaming backward into space like the tail of a comet. Kelt 9b is less a planet than a glowing shard of atmosphere, a reminder that even gravity's grip can melt under too much starlight. How do such systems come to be? The explanation points again to the chaos of birth. When a star forms in a cluster nearby, stars tug at its protoplanetary disk, warping it. Later, as massive planets grow, they can scatter one another through gravitational duels. A close encounter or resonance may throw one planet into a wildly inclined orbit or flip it outright. In multi-star systems, a stellar companion can act as a cosmic lever, twisting the entire disk through what's called the Kozai or lid-off mechanism. A planet initially circling peacefully can be slowly torqued into a high-inclination path over millions of years until tides near the star shrink and lock the orbit into its final tilted configuration. These processes, disk warping, planet-planet scattering, and companion torque, explain the variety we see today. Some planets orbit polar to their stars, circling over the poles like moons around a globe. A few even travel backward, bound by the same gravitational law that governs everything else, yet using it to chart their own path. Statistically, the surprise is not that such misalignments exist, it's how common they are. Roughly a third of measured hot Jupiters show significant tilt. Some 10% may be outright retrograde. What we once considered the natural order, the elegant disk-lined harmony of our solar system, is increasingly rare. Our home appears to be the exception, a cosmic clockwork in a gallery of pinwheels. There is something humbling, almost spiritual in this realization. We evolved beneath a sky that seems orderly because our own system is unusually calm. But the broader galaxy is a storm of eccentric worlds, planets racing above and below their suns, some baking sideways, others frozen in permanent dusk, their orbits carved by ancient collisions and chance. It is as if creation experimented endlessly with geometry before settling on the fragile symmetry we inhabit. Each tilted world is a signature of the universe's restless creativity. Their misalignments are not mistakes. They are memories, echoes of the violence that builds stability. When we look at HAT P7b shimmering over its shaking star, or at Kelt 9b bleeding metal into the void, we are seeing not disorder but diversity. And behind that diversity lies a quiet truth. Cosmic order is the rarest state of all. Our solar system, serene and flat, may be the exception precisely because it survived its chaos without losing balance. Every backward, tilted and burning world out there reminds us how precarious that serenity is, and how extraordinary it is that we orbit in the narrow calm between fire and darkness. Next comes the final question. This diversity demands, if so many worlds defy alignment, what keeps them together at all? What hidden architecture maintains the cosmic dance when symmetry fails? That is the mystery awaiting beyond the statistics where motion itself becomes the architect of harmony. Sometimes it isn't the planets that misbehave, it's the stars themselves. When stars form in pairs or clusters, their gravity can twist and tug at the fragile disks that cradle newborn planets, bending them out of alignment before worlds even begin to take shape. In such places, motion learns rebellion from birth. The universe doesn't start flat, it must fight to become so. To understand this celestial distortion, imagine two stars bound together in a wide orbit, one bearing a planet-forming disk, the other wandering in slow procession far beyond the outer edge. Every few thousand years, the companion star swings by, pulling ever so slightly on the disk's outskirts. The disk feels this uneven gravity like a ripple in a pond, and over time the ripples build into a slow procession, a gentle, relentless torque that tilts the entire structure. This process, known as the Kozai-Leadoff mechanism, is one of the galaxy's quiet sculptors. First described in the 1960s by Yoshihide Kozai and Mikhail Leadov, it explains how a distant gravitational companion can trade inclination for eccentricity in a rhythmic cycle. A planet orbits peacefully for millions of years, then the companion star's pull nudges its orbit higher and higher until, like a pendulum, the tilt peaks and the path stretches into a long ellipse. When the inclination drops again, the ellipse collapses and the cycle repeats. In some systems, this oscillation becomes so extreme that the planet's orbit flips entirely, transforming a once orderly path into a retrograde loop. Gravity and its slow arithmetic can turn alignment into opposition without ever breaking the rules. The consequences are breathtakingly diverse. In binary systems where the companion star sits at just the right distance, hundreds to thousands of astronomical units away, the Kozai-Leadoff effect can send planets plunging toward their host stars. The tidal forces circularize their orbits into tight, blistering embraces, creating the class of hot Jupiters that dominate exoplanet catalogues. Others are thrown outward, frozen in eccentric limbo, or ejected entirely to drift as rogue planets between the stars. Even if no planets yet exist, the same dynamics can warp the protoplanetary disk itself, forcing it to precess, twist, or even tear into misaligned layers. Some disks now observed by ALMA, such as those around the stars GW Orionis and HD 142 FUM 277, show dramatic rings tilted by tens of degrees, evidence that Kozai-Leadoff sculpting begins before planets are born. In those twisted nurseries, new worlds inherit crooked cradles. They form already tilted, preloaded with the inclination that will later evolve into strange polar or retrograde orbits. The misalignment isn't rebellion, it's heritage. The star tilts, and its children follow. But binary partners are not the only culprits. Stars rarely form alone. They are born in dense clusters where hundreds of siblings pass within light years of one another. Each close encounter is a gravitational whisper that can warp a disk, steal comets, or alter planetary orbits. Simulations show that in the first few million years of a cluster's life, these flybys can tilt disks by 30, 60, even 90 degrees. If the encounter is close enough, it may strip the disk entirely, scattering planet-forming material into interstellar space. The survivors become systems with warped planes and wandering inclinations, cosmic mosaics of distortion left by an early crowd. Modern astronomy is beginning to measure these once invisible scars. The Gaia mission, mapping the precise motions of over 2 billion stars, has transformed our understanding of how stellar encounters shape planetary systems. Gaia's data allows astronomers to trace the orbits of nearby stars backward in time, identifying close approaches that may have brushed the Sun's own outer regions. Already, scientists have catalogued hundreds of past and future stellar flybys, including Schultz's star, which grazed the Oort cloud 70,000 years ago, and LISA 710, predicted to pass within Uranus 6, light years just 1.3 million years from now. Such events, though rare on human scales, are common in stellar history. Each one can shuffle the orbits of distant comets tilt outer planets, or leave subtle imprints on the architecture of a solar system. Gaia's statistics imply that the average star in our galaxy experiences multiple significant encounters during its lifetime, enough to warp any planetary nursery more than once. It is no wonder then that so many exoplanets orbit askew. The universe taken as a whole is not a clockwork, but a sculpture in motion, carved by the mutual gravity of stars brushing past each other across epochs. Viewed this way, misaligned worlds are not anomalies, they are memories of encounters. Each tilt is a fossil of a gravitational conversation between suns, each retrograde orbit a record of something that once passed close enough to matter. The galaxy is a web of such encounters, threads tugging threads, producing systems as individual as fingerprints. Perhaps it's only chance or a rare calm neighbourhood in the Milky Way's spiral arm that allowed our own solar system to stay relatively flat and stable. Most planetary families grow up in turbulence, their orbits scarred by the touch of passing stars. Yet even in that chaos, a pattern emerges. When stars tilt their children, they do not destroy them, they diversify them. The cosmos learns its shapes through interaction, not isolation. Every warped disk, every polar orbit, every backward planet is a reminder that the universe is not still, it is social. Gravity is its language, and through it every star leaves a trace in another's sky. The next chapter follows those traces outward to where tilted systems and wandering bodies drift beyond the last pull of their parent suns into the interstellar deep. Their order dissolves entirely, and the question becomes not how systems form, but how they end. Even the strangest orbits, backwards, sideways, chaotic, follow the same rulebook. There are no exceptions, no loopholes, no cosmic rebels who truly disobey. Gravity is impartial. Whether a world moves with its star or against it, the same mathematics governs its dance. Every retrograde spin, every tilted plane, every eccentric ellipse still curves along the quiet logic of Newton and Einstein. In the simulations, this truth becomes visible. Astronomers model whole planetary systems, some aligned, some shattered, letting them evolve over billions of virtual years. At first, the scenes look like turmoil, planets crisscrossing inclinations, climbing orbits, twisting into strange geometries. But as the clock runs forward, a deeper order emerges. Even when half the worlds are retrograde, the system settles into coherence. Mutual resonances form energy trades, but never disappears. The chaos folds inward like a wave-finding rhythm. The computer's gravity maps glow with faint spirals of stability, islands of order inside apparent disorder. In one such simulation from the Max Planck Institute, a star with 5 planets begins in a disarray of random tilts. 2 flip completely orbiting backward, yet after 1 billion years all 5 remain bound, the ensemble rotating in a slow procession that keeps their separations intact. Another visualization from NASA's Exoplanet Dynamics lab shows a cluster of tilted gas giants, each on a different plane, tracing luminous rings that shimmer but never collide, an intricate cosmic mobile turning every which way, but always returning to balance. It's not symmetry that preserves them, it's the conservation of energy and momentum, the unwavering fairness of gravity's pull. This is the heart of the universe's philosophy. Symmetry is optional, coherence is inevitable. The cosmos does not require everything to face the same direction. It only asks that each motion remember its relationship to the whole. A backward planet still contributes its angular momentum to the system. A tilted orbit still participates in the shared center of mass. Together they make not chaos but complex harmony, a fugue instead of a melody, bound by physics instead of preference. The impartiality of gravity is both stern and compassionate. It makes no distinction between light and dark, prograde and retrograde, order and disorder. It pulls on every atom with the same invisible patience, turning difference into pattern. In that fairness lies freedom. The universe allows every possible orientation, every variation of motion, yet still weaves them into a single continuous structure. Nothing escapes the law, but within it, everything is allowed. Think of it this way. The sun's light divides the solar system into day and night, but its gravity does not choose sides. It binds Jupiter, which spins swiftly forward, and Venus, which drifts slowly backward with the same devotion. It accepts Uranus rolling on its side as easily as it holds Earth upright. Their directions differ, their obedience does not. The symmetry may be broken, but the relationship endures. We often imagine the universe as an architect of perfection, aligning everything in elegant planes and circles. But perhaps perfection was never the goal. Perhaps the beauty lies in the forgiveness of asymmetry, the way gravity lets every orbit, no matter how misplaced, find a home within the same fabric of motion. Retrograde systems are not mistakes. They are proof of universality. They show that the laws of nature are broad enough to include reversal, that coherence does not need conformity. If you could step back and see the galaxy from afar, not in light but in motion space, you'd witness a sculpture of perpetual compromise. Planets, stars, comets, and dust all moving in directions that seem random up close, but together form a statistical grace. Retrograde and prograde tilted and true, they weave a web of gravitational equality. No single motion defines the system, the sum of all motion does. And as you watch, you might realize that the universe is not obsessed with order, it is invested in continuity. The same force that curves an apple's fall also steers galaxies through space, and it cares nothing for direction. It simply connects. In that connection, we find the final symmetry, not geometric, but moral. A symmetry of participation, where every body forward or backward, near or far, contributes to the same unbroken whole. Gravity's impartial hand writes the same equation for everyone. It is the quiet author behind both the chaos and the calm. Next, we follow that hand outward to the galactic scale, where trillions of these individual orbits combine into one grand rotation, and the same law that shapes comets and planets turns entire star systems into spiral arms of motion. When we look out from Earth, our solar system seems serenely arranged planets spaced like notes on a musical staff circling in stable harmony for billions of years. But that quiet is earned, not innate. Beneath its calm lies the memory of upheaval, migrations, collisions, and expulsions that shaped a system capable of surviving its own chaos. The story of how order emerged from turmoil is written in a model named almost modestly for the city, where it was first conceived Nice, on the coast of France. In the early 2000s, a group of planetary scientists Alessandro Morbidelli, Rodney Gomez-Hal Leveson, and Cleomenis Tsaganis proposed what became known as the Nice model. It reimagined the solar system's youth not as a slow settling of orbits, but as a dramatic reshuffling, a celestial reconstruction that turned instability into balance. According to the model, the giant planets Jupiter, Saturn, Uranus, and Neptune did not begin where they are now. They were born much closer together, embedded in a dense disk of leftover ice and rock beyond the orbit of Saturn. For hundreds of millions of years, they interacted gravitationally with that debris tugging on it, scattering it, and in return being nudged themselves. Then came the tipping point, a resonance between Jupiter and Saturn, likely a 2-1 orbital resonance, where Saturn completed one orbit for every 2 of Jupiter's destabilized the entire outer system. Jupiter was flung slightly inward, Saturn outward, and the smaller ice giants Uranus and Neptune were kicked into a migratory cascade. In their wake, they hurled countless planetesimals across the solar system, triggering what we now call the Late Heavy Bombardment. That bombardment left scars we still see today, the pocked face of the Moon, the craters on Mercury, and the ancient basins on Mars. But it also performed an act of purification. By scattering the leftover debris, the giant planets cleared the stage for long-term stability. Objects that might have perturbed the inner planets were either ejected into the Oort cloud or thrown out of the solar system entirely. In this violent pruning, chaos created endurance. The solar system's current architecture, 4 rocky worlds close to the Sun, a stable belt of asteroids, and 4 giants on near-circular paths emerged from that single episode of disorder. The Nice model also explained several enduring puzzles. It showed how Neptune's outward migration could have captured Pluto and other Kuiper belt objects into resonant orbits, hence Pluto's peculiar 3:2 resonance circling the Sun twice for every 3 of Neptune's years. It revealed why the Kuiper belt itself is sharply truncated beyond 50 astronomical units, and how Jupiter's inward jump stabilized the asteroid belt by ejecting most of its mass. Even the strange backward motion of some Trojan asteroids near Jupiter's Lagrange points may be echoes of that primordial reorganization. Recent missions have turned this model from theory into tangible evidence. NASA's Lucy mission, launched in 2021, is on its way to visit Jupiter's Trojan asteroids, the thousands of small bodies trapped in stable gravitational pockets ahead of and behind Jupiter's orbit. They are in essence fossils of the Nice model's migration event, remnants of the planetesimal swarm that once roamed the early solar system. By studying their composition, shapes and densities, Lucy aims to reconstruct the ingredients of the primordial disk, the raw materials that Jupiter and its siblings once scattered across the void. Even from afar, early observations from Lucy's instruments have refined our understanding of the Trojans. Infrared scans suggest some may contain complex organics and water-bearing minerals materials similar to both comets and outer belt asteroids. That diversity hints that they did not all form near Jupiter, but were captured from multiple regions during the giant planet's migrations, a frozen cross-section of the solar system's chaotic adolescence. The spacecraft's eventual flybys set for the 2030s will give us a moving museum exhibit of how stability was built from debris. Computer models continue to reinforce the Nice scenario with refinements. Recent simulations at the Southwest Research Institute and CNRS indicate that the solar system's current stability depends sensitively on Jupiter's exact migration distance. Had it shifted just a few percent more inward, it might have destabilized Mars or ejected Earth from its life-friendly orbit. Had it moved less, Neptune might never have reached its current region, leaving the outer solar system a cluttered, unstable expanse. The razor-thin line between chaos and coherence runs through those ancient gravitational exchanges, a reminder that our calm is statistical, not guaranteed. The philosophical weight of the Nice model lies in its paradox: stability was born of instability. Order did not precede chaos, it emerged from it sculpted by the very violence that threatened to erase it. The planet's serene, modern motions are the survivors of a vast sorting process, a self-organizing system that pruned everything that could not last. Even now, their orbits are not perfectly still. They oscillate minutely, tugged by one another, breathing in cycles millions of years long. But within those oscillations lies resilience, not fragility. The architecture of survival is dynamic equilibrium, not frozen perfection. When we look at the calm solar system today, we are seeing the aftermath of a storm that never truly ended, it simply learned rhythm. The same law that allows Jupiter to tilt the early disk and scatter worlds also allows it to hold those remaining worlds together forever after. The Nice model is not just a story of physics. It is a parable of endurance, the understanding that harmony is not the absence of conflict, but the refinement of it. And as the Lucy mission coasts toward its targets, silent sunlit gliding through the same gravitational pathways carved billions of years ago, it carries that lesson forward. Every Trojan it visits is a relic of chaos that learned to orbit quietly. Every measurement it makes whispers the same truth: we live in a system that survived itself. Every stone that falls from the sky is a page torn from the beginning of the world. Long before continents drifted or oceans formed, long before life thought to look up, the solar system wrote its autobiography in rock and dust and scattered copies everywhere for us to find billions of years later. These fragments, meteorites, asteroidal shrapnel, cometary grains, are more than geological curiosities. They are the cosmic record in stone, each one carrying the signature of a time when everything was molten, violent and new. In the earliest moments after the sun ignited, the protoplanetary disk was not the calm spiral of textbook diagrams. It was a boiling storm of gas and mineral vapor threaded with magnetic turbulence. Temperatures near the infant sun reached thousands of degrees, vaporizing silicates and metals. Farther out, water, carbon dioxide and methane froze into ice. Between these extremes, shock waves from solar flares and early planetary collisions created zones of rapid heating and cooling. Out of that chaos condensed the first solids, the calcium-aluminum-rich inclusions CEIs found in primitive meteorites. Each grain crystallized in that fiery fog 4.567 billion years ago, making them the oldest known materials in the solar system. Every isotope ratio etched within them, oxygen, magnesium, aluminum, records the sun's first breaths. These grains drifted outward through the turbulent gas, mixing with colder ices from the far reaches of the disk. That mixing, driven by magnetorotational instabilities, stellar winds and shock fronts, blurred the boundary between inner and outer worlds. Iron from the core-forming regions mingled with frozen carbon from the Kuiper belt. Silicates from near the sun fused with nitrogen compounds from the edge of darkness. The chemistry of our planets was stirred like a cosmic cauldron, uniting extremes into one recipe for life-bearing matter. We know this because the evidence keeps falling at our feet. Meteorites that land on Earth carry isotopic fingerprints linking them to that ancient turbulence. Carbonaceous chondrites, the most primitive of all, contain hydrated minerals and amino acid precursors molecules that once swam in the same nebula broth as Earth's raw ingredients. Their isotopic ratios of oxygen and nitrogen match those of comets, and the Sun's atmosphere showing that every planetary body, no matter how distant, draws from the same chemical canvas. The Allende meteorite, which exploded over Mexico in 1969, remains a classic example. Inside its blackened crust lie glittering inclusions older than Earth, carrying traces of extinct isotopes such as aluminum-26, a radioactive element that once heated newborn planetesimals from within. These isotopes tell us that the solar system's birth was not isolated. It was likely triggered by a nearby supernova, whose shockwave injected those short-lived elements into the collapsing cloud. Even our beginnings were interstellar, borrowed from the death of another sun. Modern missions have extended this record beyond chance impacts. In 2023, NASA's OSIRIS-REx returned to Earth, carrying samples from the asteroid Bennu, a 500-meter-wide time capsule left untouched since the solar system's infancy. Analyses at laboratories in Houston and Tokyo revealed carbon-bearing minerals, phosphates and water locked in clay, evidence that even small bodies once interacted with liquid water and organic chemistry. The isotopic signatures of hydrogen in Bennu's minerals match those found in certain carbonaceous meteorites, confirming that the asteroid belt and Earth share a common ancestry of volatile rich material. The same primordial dust that built our oceans still circles the Sun as rock. Elsewhere, Japan's Hayabusa 2 mission brought back samples from Ryugu, another carbonaceous asteroid, and found amino acids identical to those in meteorites. Each mission confirms a truth that grows harder to ignore. The chemistry of life was never confined to one planet. It was written into the ingredients of the solar system itself long before Earth assembled from its fragments. When scientists analyze these samples with mass spectrometers, they are essentially listening to the echo of the solar nebula. Every isotope ratio, oxygen, 16 to oxygen, 18 deuterium to hydrogen, nitrogen, 15 to nitrogen 14, plays a note in a universal melody. Across meteorites, comets and planets, that melody repeats with subtle variations like a theme, woven through different movements of the same symphony. The hydrogen in your bloodstream and the carbon in your breath once belonged to that same turbulent cloud. The iron in the core of the Earth and the metal in a meteorite that burned above the Sahara were once neighbours in the same eddy of gas swirling around the young sun. The unity of that chemistry is astonishing precisely because it was born from chaos. Turbulence, collisions and radiation were not enemies of order. They were the means of mixing that ensured no planet formed alone in isolation. Every act of violence in that early epoch was also an act of connection, spreading heat, light and matter across space until the system shared one signature. Hold a meteorite in your hand, its surface melted black, its interior flecked with nickel and olivine, and you're holding a piece of the first stable thing the solar system ever made. You can feel the weight of 4.5 billion years, and the paradox it carries that from the random storm of the nebula came a single chemistry, a shared ancestry that links every planet, moon and living being. The cosmic record in stone is a testament to that unity. It says you were never separate from the stars. Every grain of dust that built your body was once part of that swirling incandescent cloud that also built Jupiter's storms, Mars's deserts and Saturn's rings. We are quite literally made of the same turbulence that almost tore the solar system apart, and because of that we endure together. From chaos came connection, from dust a family. And the stones that fall through our skies are the universe reminding us of both. Perfection is beautiful, but it cannot last. In celestial mechanics, the most delicate truth is this: a perfectly symmetrical system is also the most fragile. The solar system endures not because everything is aligned, but because it isn't. Tiny imbalances, fractions of mass, minutes of inclination, slivers of eccentricity are what keep the planets alive in motion. Imperfection is not a flaw in the cosmic design. It is the design. NASA's long-term dynamical simulations make this paradox visible. At the Jet Propulsion Laboratory, supercomputers model billions of years of orbital evolution, tracking how every planet, asteroid and moon influences every other. When they begin with a perfect system, planets spaced evenly, orbits circular inclination 0, the harmony collapses within a few million years. Resonances line up too precisely, amplifying each other until chaos explodes. One planet drifts inward, another outward. Collisions or ejections follow. It is symmetry itself that breaks the system. But introduce slight offsets, a few degrees of tilt, a bit of orbital eccentricity, and the pattern stabilizes. Resonances no longer coincide. Oscillations disperse energy instead of reinforcing it. The result is long-term coherence, like a choir slightly out of tune that still finds a richer, warmer sound. The same principle holds across scales from the wobbles of Jupiter's moons to the motion of entire galaxies. Asymmetry dissipates tension. It allows motion to breathe. In 2021, JPL's Systems Dynamique Integral simulations reveal that Earth's orbit, though nearly circular, subtly oscillates between 0.016 and 0.07 in eccentricity every 100,000 years. Those tiny variations driven by gravitational tugs from Venus and Jupiter modulate our climate through the Milankovitch cycles. Without them, weather would stagnate, seasons would fade, and the planet's energy balance might drift into runaway extremes. Our world's capacity for change, ice ages and renewals, deserts and forests is born from those imperfections. In geometry, a flaw is a deviation. In nature, it is a pulse. The same lesson emerges from Saturn's rings. High-resolution data from the Cassini mission showed that the rings are full of spiral density waves, ripples induced by the slight eccentricities of Saturn's moons. Were those moons perfectly circular in orbit, the rings would flatten dull and eventually collapse inward. Instead, they shimmer with constant renewal, a living record of a symmetry-feeding order. In the broader architecture of the solar system, imperfection is the safety valve against resonance catastrophe. Jupiter and Saturn, for example, hover near but not exactly at a 5-2 orbital resonance. That small mismatch diffuses their gravitational influence, preventing destructive synchronization. Had their orbits been perfectly resonant, the Nice model suggests the result would have been catastrophic. Inner planets scattered, the asteroid belt shredded beyond recognition. Instead, their near miss preserves balance through restless stability, a harmony born of tension, not stillness. Modern exoplanet simulations from NASA's Exoplanet Science Institute confirm the same pattern. Planetary systems with small misalignments and eccentricities live longer than those built in ideal symmetry. A slight tilt spreads out gravitational interactions, reducing destructive feedback. Perfection, ironically, leaves no room for adjustment. A flawed system can adapt. There's a poetic echo here that transcends physics. The Japanese art of kintsugi repairs broken pottery, with veins of gold turning fracture into beauty. The cosmos does this with gravity. Every misaligned orbit, every tilted axis, every retrograde spin is a golden seam sealing the universe against its own brittleness. Perfection would freeze. Imperfection lets it move. Even the galaxies, those vast spirals of stars, owe their arms to slight asymmetries in their mass distribution. A galaxy too symmetrical would spin down into featureless smoothness. A touch of unevenness gives it form, texture, life. Think of the planets again, circling not in perfect rings but in ellipse, each one slightly stretched, slightly inclined, whispering the story of its formation. Those imperfections prevent resonance lock, allow tides to shift, let moons dance without colliding. The solar system's endurance is a direct result of its small errors. Every wobble, every deviation, every irregularity is part of the rhythm that keeps it from unraveling. Perhaps this is the deeper symmetry of the universe, that the only stable perfection is imperfect. That harmony is not a static chord, but a continuing negotiation between forces that never fully agree. When scientists run their perfect models and watch them collapse, they are seeing what the universe long ago decided to avoid: the silence of exactness. Instead, it chose variance, dissonance, and the soft blur of real motion. So when we gaze at the sky and see planets slightly tilted, orbits slightly oval, and moons that wander, we're not seeing errors in design. We are seeing design through error, the deliberate looseness that makes time possible. The beauty of the solar system lies not in how precisely it was made, but in how gracefully it endures its own imbalance. Perfection breaks, flaw endures. And that endurance, measured in billions of years, is the universe's quiet definition of harmony. Step back far beyond the orbit of Neptune, past the cometary halo, past the quiet edge of the heliosphere, and the pattern continues. The solar system's flattened disk is no isolated accident. It is a fractal behavior echoed at every scale the universe has ever built. Wherever gravity gathers matter, it also teaches it to spin. From collapsing clouds to spiral galaxies, from storm systems to clusters of galaxies, the same equations whisper the same result. When chaos falls inward, it remembers the twist. In the beginning, the newborn cosmos was nearly uniform, a sea of hydrogen and helium with tiny quantum wrinkles, fluctuations in density no greater than 1 part in 100,000. Those slight imperfections, magnified by gravity and time, seeded the web of galaxies we see today. Each overdense region began to collapse, and as it did, angular momentum, tiny initial rotations from those early fluctuations, became amplified. The mathematics is universal. When a rotating object contracts, it spins faster. The same principle that turns a skater's slow twirl into a blur of motion forged the spin of stars, planets, and ultimately entire galaxies. What results is not just order, but recurring geometry. A spiral galaxy is a solar system scaled up to 1 trillion-fold. Its spiral arms, the stretched aftermath of angular momentum preserved through cosmic time. Look at NGC 1300 or M51, the Whirlpool Galaxy, and you see the same dance written large gas and dust compressed into a thin disk, stars orbiting a common center, collisions damped by time until the chaos becomes pattern. It is the same flattening that shaped Saturn's rings, the same logic that thinned our solar nebula. Nature recycles its architecture, only the scale changes. Modern cosmology has begun to map this hidden order with astonishing precision. Surveys like Sloan Digital Sky Survey, SDSS Euclid and Gaia DR3 reveal that galaxies are not scattered randomly in orientation. Their spins show statistical alignments across millions of light-years correlated with the cosmic web, the vast network of filaments and voids that connects galaxy clusters. Simulations such as Illustrious TNG and Eagle reproduce this naturally. Gas streams along the filaments of dark matter spiraling inward as it feeds forming galaxies. Low-mass galaxies tend to align their spin along the filament that birthed them, while massive ones flip and spin perpendicular as mergers reshape them. It's angular momentum on a continental scale sculpting cosmic architecture the same way the solar nebula sculpted planets. In the Millennium simulation, a cube of universe, 500 million light-years wide, the same pattern appears: billions of miniature whirlpools rotating in synchrony with their filaments, their internal disks flattened by the same balance of collapse and rotation that made our ecliptic plane. Statistical chaos gives rise to aesthetic coherence. Even when galaxies collide, a dance of destruction. Spanning hundreds of millions of years, the result is almost always a new rotating system. Destruction is just pattern reassembling itself. Angular momentum is the universe's memory and inheritance passed from scale to scale. The spin of the Earth traces back to the rotation of the solar nebula, the Sun's spin to the rotation of the Milky Way's progenitor cloud, the Milky Way's spin to the torque of dark matter filaments stretching across the early cosmos. Every turn is a descendant of that primordial swirl impressed upon matter at the moment of recombination. And even now, when cosmologists measure the polarization of the cosmic microwave background, they find faint imprints of that same angular structure, ripples in temperature and direction, that tell us the first light of the universe already carried the signature of rotation. If the universe had begun in perfect symmetry, no twist, no asymmetry, it might have collapsed in on itself or remained a featureless fog. Instead, those minute variations in density and spin gave rise to everything: stars, planets, galaxies, and us. Imperfection became organization, rotation became architecture. It's humbling to realize that the equations governing a collapsing dust cloud in a telescope's image are the same that describe the birth of a galaxy. Conservation of angular momentum, gravitational instability, viscous damping, simple principles infinitely reinterpreted. The universe doesn't invent new rules for every scale. It prefers to repeat motifs. A spiral arm is just a planetary disk written in millions of light years. A binary star's tilt is a galactic merger in miniature. When viewed across time, the cosmos reveals itself not as chaos tamed, but as pattern made self-similar. There is poetry in that repetition. The same dynamics that flattened dust into the ecliptic also sculpted the Milky Way's shining arms that arc above us each night. We live within one of those patterns nested whirlpools of motion, each remembering the one that came before. The Sun orbits the galaxy once every 230 million years, carrying its planets like embers in a slow, majestic swirl. From a distant vantage, our solar system is just another glint in the galactic disk, one node in an endless chain of spinning hierarchies. Order, then, is not imposed. It is inherited. The cosmos prefers pattern, because pattern is the only way chaos can endure. From the tilt of a comet's orbit to the rotation of a galaxy cluster, the same ancient twist runs through everything. Motion is the handwriting of creation, and across 13.8 billion years, the handwriting has not changed. In that realization lies a quiet symmetry. The solar system's gentle flatness, the galaxy's spiraling arms, the filaments of the cosmic web, all are stanzas of one poem repeated in greater and greater scales, and through every verse the same refrain: when matter falls, it spins. When it spins, it finds shape, and in that shape the universe remembers itself. The sun looks eternal, an unwavering gold circle in the sky, but beneath that calm face it breathes. Not in air, not in heat, but in magnetism. Every 11 years the solar heart reverses its pulse. Magnetic north becomes south, south becomes north. It is the slow inhalation and exhalation of a living star. Through that cycle of reversal, storms ignite, flares leap, and fields twist and heal again. The rhythm that began in a swirling cloud billions of years ago continues now translated into light plasma, an invisible force. At first glance, the sun seems simple, a sphere of glowing hydrogen fusing into helium, but its surface is anything but uniform. The equator spins once every 25 days, while the poles take nearly 35. This differential rotation means the sun's plasma shears and drags at its own magnetic field, stretching lines of magnetism like taffy around its circumference. Eventually these field lines tangle and knot. Sunspots bloom where magnetic flux pierces the surface, creating regions cooler and darker than their surroundings. Solar flares burst when those knots snap. Each eruption flings billions of tons of plasma into space, sending shockwaves across the heliosphere. To every planet, Mercury, Earth, Neptune, those waves are whispers of the sun's restless heartbeat. In the early 17th century, Galileo Galilei was the first to sketch those dark spots, thinking them blemishes on perfection. Centuries later, we know they are the lungs of the sun, evidence that a star's serenity is forged by motion, not the absence of it. Modern science has made this breathing visible. NASA's Parker Solar Probe and ESA's Solar Orbiter now fly through the furnace itself within tens of millions of kilometers of the surface. Their instruments map the magnetic architecture in exquisite detail. Solar Orbiter's polarimetric and helioseismic imager PHI has confirmed what theory long suggested. Magnetism originates deep in the tachocline, the boundary where the radiative zone meets the convective zone. They're superheated plasma churns like a global ocean, creating vast electrical currents. The resulting dynamo effect weaves magnetic fields that rise through the sun's surface like smoke through water. When they emerge, they loop and reconnect, releasing titanic bursts of energy known as coronal mass ejections. The Parker probe, flying closer than any craft before it, has revealed the sun's magnetic field as a sea of switchbacks, zigzagging reversals that ripple outward through the solar wind. These switchbacks are the solar breath made visible waves of magnetism that accelerate particles and shape space itself. In those moments, the sun stops being a passive ball of fire. It becomes a living engine of electromagnetism, sculpting an invisible bubble that extends beyond Pluto. Every 11 years, this entire system flips. The solar magnetic cycle, first recorded by astronomers in the mid-1800s, shows a rise and fall of sunspot activity, an awakening and a rest. At the peak, magnetic fields are most tangled. At the trough, they are newly reordered. After each reversal, the sun's magnetic poles swap places, beginning the next heartbeat. These oscillations drive the heliospheric current sheet, a wavy membrane of electric charge that sweeps through the solar system. The Earth crosses it regularly, a gentle reminder that our planet lives within a dynamic electromagnetic sea. To see the beauty in this is to recognize a pattern repeated everywhere in nature: chaos, giving rise to order, tension, releasing into balance. The sun's surface may look like turmoil loops, flares, spirals, but that turbulence is the mechanism of equilibrium. Magnetic fields twist until they can no longer hold, then snap and realign, releasing energy that prevents deeper instability. It is self-regulation by fire. ESA's Solar Orbiter has now imaged the solar poles long hidden from our view, where the roots of those field lines emerge and reconnect. Scientists call them the switch points of the sun's soul. Their magnetic streams rise, fade, and reform, feeding the next cycle. Every flare we see, every aurora on Earth, every charged particle sweeping through interplanetary space traces back to those silent polar motions. The sun is not a static furnace. It is a cosmic heartbeat, balancing creation and destruction with every magnetic breath. When we witness auroras dancing across polar skies, we're seeing the conversation between our world and that breathing star. Electrons born in solar flares days earlier spiral down Earth's magnetic field lines, painting the night in green and violet. It is the same dialogue of magnetism and motion that began 4.5 billion years ago. Every shimmer in those lights is a syllable in the sun's long exhalation. In the rhythm of these cycles lies a profound metaphor: stability through renewal, order through flux. The sun never freezes into perfection. It maintains its serenity by continuously destroying and remaking its magnetic self. Galaxies spin, planets orbit, atoms vibrate, all following the same truth that the sun embodies: motion prevents decay. Stillness is the only real chaos. The solar orbiter's data are more than science. They are a lesson. Every reversal, every flare, every quiet return to calm shows that the universe's heartbeat depends on the courage to change direction. The sun's magnetism is not random fury. It is the language of balance written in plasma. It reminds us that the cosmos sustains its harmony not by avoiding chaos, but by breathing through it. And with each sunrise, that breath continues, lighting a world that survives inside its gentle storm. When you look at the solar system today, planets gliding in calm orbits, moons circling faithfully, the sun rising without fail, it's easy to imagine it has always been this serene. But peace in the cosmos is not the absence of violence. It is the result of it. Every stable orbit, every rhythmic spin, every symmetrical ring was once born from collision, upheaval, and the long patience of gravity. The beauty we see now is not pristine, it is recovered, a harmony earned, not given. In the beginning, there were no clear paths, no stable planes, only a cloud collapsing, crashing into itself. Fragments collided, shattered, and reformed. Every impact created heat, shock, and debris. Every loss of symmetry became the seed of a new balance. Venus turned backward. Uranus fell sideways. The moon tore itself free from the Earth. Triton was captured and reversed its orbit. Comets fell from the darkness. Asteroids broke and scattered, filling the voids between worlds. And yet through billions of years of this cosmic storm, something remarkable emerged: coherence. Not perfection, but resilience, a geometry that could survive its own chaos. The story of the solar system is one of restoration through motion. Each collision wrote a scar into gravity's memory. Each scar became structure. Every planet's tilt, every moon's orbit, every belt of debris preserves evidence that violence was not the end of order, but its teacher. The universe, it seems, does not strive to avoid disruption. It uses disruption as a tool to sculpt endurance. NASA's dynamical reconstructions show that after the chaos of formation, the so-called Nice model epoch, the orbits of the giant planets slowly stabilized. Their mutual resonances, once destructive, began to synchronize just enough to avoid catastrophe. The result was a slow choreography: Jupiter's gravity shaping the asteroid belt, Saturn tuning its rings, Neptune guiding icy wanderers at the edge of night. What was once random became rhythmic, and what allowed that rhythm to persist was imperfection, slight tilts, uneven masses, minor eccentricities that absorbed and diffused energy. Over billions of years, these irregularities acted as cushions, preventing the system from ever locking into a fragile, perfect symmetry. Just as a heartbeat depends on contraction and release, the solar system endures through its asymmetry, a kind of dynamic symmetry, alive and adaptive. Gravity and time are its composers, collisions are its percussion. The result is not a static design, but a symphony in motion. Consider Earth, born of impact, stabilized by its moon, balanced by tides that slow its spin and steady its tilt. Without that single catastrophic collision, 4.5 billion years ago, the one that created the moon Earth might have tumbled chaotically like Mars, or frozen in tidal lock like Mercury. Instead, from that disaster came seasons, climate, and the delicate rhythm of life. Collision became symmetry. It's a pattern repeated across the cosmos. Venus, Uranus, Triton, and retrograde asteroids, all outliers that remind us balance is not uniformity, but endurance through difference. The same forces that broke them also bound them. Gravity forgives nothing, yet it wastes nothing. Every blow, every misalignment, every reversal finds a way to become part of the whole. Over immense timescales, this principle reveals itself as a kind of cosmic compassion. What appears violent in a human lifetime is gentle across billions of years. A shattered planetesimal becomes a meteor that brings water. A tilted axis becomes the reason for warmth and winter. A captured moon becomes the reason a planet's rotation stays steady. The solar system endures not because it resists change, but because it evolves with it. Time itself is the quiet craftsman here. Given enough of it, gravity smooths sharp edges, energy disperses, and chaos folds into pattern. NASA's and ESA's simulations show this transformation vividly, an early solar system of ricocheting orbits slowly converging into the serene architecture we know. From violence to design, from collision to symmetry, the same transition happens in galaxies, in atoms, even in the sun's own magnetic heart. Everywhere, nature follows one law: motion refines itself into form. If you could accelerate time and watch the entire history of the solar system unfold in a single minute, you would see it breathe. Worlds would bloom, collide, tilt and settle. Dust would flare into light, collapse and rise again. And at the end of it all, out of all that motion and turmoil, you'd see what we see tonight, a system of silent harmony, each world tracing its ancient path with precision, none colliding anymore, all remembering where they came from. This is the quiet triumph of the cosmos, that even destruction can serve creation, that chaos can be a midwife to beauty, and that imperfection over time becomes design. So the next time you look at the night sky, remember every orbit, every tilt, every rotation is a scar that healed well. The universe endures not because it avoids impact, but because it turns impact into rhythm. From collision to symmetry, from violence to balance, that is how order survives. That is how the universe keeps time. Close your eyes for a moment and imagine the solar system not as a map, but as a feeling, a soft balance turning. Every planet, every moon, every drifting stone moving through space as if following a breath that began long before there was air to breathe. They do not move in perfect circles. They do not share one flawless plane. They wobble, lean, tilt, and because of those small deviations, they endure. The quiet order of imperfect worlds is the most delicate harmony the universe ever wrote. Flat enough to hold together, yet uneven enough to stay alive. Each orbit slightly off, each rotation a little crooked. Mercury's incline, Earth's tilt, Pluto's wandering path, they are not errors in design. They are the fingerprints of reality, the scars of creation still warm with memory. If the solar system were perfectly aligned, it would be brittle, one perfect glass bowl waiting for the first crack. Instead, it's a mobile of worlds, each one swaying just enough to keep the others in motion. Balance through imperfection, peace through difference. It all began with that first spin, the silent rotation of a collapsing cloud, a tiny twist perhaps born from a chance asymmetry in the Milky Way's gravity, and that single motion, that faint imbalance, became the foundation of everything. Stars, planets, oceans, seasons, the turning of days. We are each of us children of that rotation. The angular momentum of the sun's birth still hums inside every atom of our bones, every molecule of air we exhale. Motion became inheritance. Inheritance became memory. And memory became pattern, not perfect, but whole. From above, the solar system looks serene, 8 planets circling in their thin golden plane. But if you could listen instead of look, you'd hear a gentle dissonance, the slight mismatches that prevent silence. The faint pull of Jupiter's gravity on Mars, the whisper of Earth's tides tugging at the moon, the slow nod of the sun wobbling as the planets tug back. It's a living equilibrium, not a static one, a harmony written not in stillness, but in perpetual adjustment. The music of orbit is not a single note. It's a chord sustained across billions of years, tuned by the interplay of mass and time. The beauty of this system lies in its refusal to be flawless, flat but not flat, aligned but not uniform, predictable yet never frozen. Even the ecliptic plane, that paper-thin sheet binding all planetary paths, wavers slightly like the surface of a pond trembling under sunlight. It reminds us that perfection is not the goal of nature. Continuity is. And continuity in a universe governed by gravity can only exist through forgiveness, the way each orbit yields a little to the next, how every force finds its counterbalance, how even collisions give rise to coherence. Carl Sagan once said that we live on a pale blue dot suspended in a sunbeam. But that dot does not stand still. It drifts through an imperfect yet persistent system, one that remembers the chaos of its birth and turns it into rhythm. Our calm is inherited from catastrophe, our symmetry born from spin. And still that first motion continues carrying us around the sun around the galaxy through the dark ocean of the cosmos. The same swirl that once gathered dust into worlds now gathers galaxies into filaments, and will keep turning long after we're gone. So tonight, when you look up and see that faint arc of the Milky Way, remember it is not perfection that holds it together, it is patience. The patience of gravity, of time, of motion, finding its balance again and again. Every planet you've ever wished upon, every comet's tail, every moonrise, all are born from that same gentle insistence of the universe to keep spinning, to never stop, to take chaos and turn it one revolution at a time into calm. The solar system's beauty isn't that it's flawless, it's that it forgives its flaws so completely that we forget they were ever there. It keeps moving quietly, endlessly, an imperfect pattern that never breaks, and as it turns, so do we, held in the rhythm of that ancient breath. Still spinning, still balanced, still alive in the quiet order of imperfect worlds. And now, rest. Let the words fade and the images drift like dust settling back into the silence from which they came. You have travelled through 4.5 billion years of motion storms of gas and light collisions and calm, and somehow you're still here breathing beneath the same laws that hold the stars. Out there, the solar system turns without pause. Each planet follows its invisible path, not in hurry, not in hesitation. Mercury races dawn to dawn. Neptune glides in a centuries-long circle. The sun hums softly in the center, its magnetism breathing in and out, guiding the entire family through the dark. Everything moves together slightly, tilted slightly, imperfect, perfectly alive. While you sleep, Earth will continue its slow spin toward morning. Jupiter's storms will spiral, Saturn's rings will shimmer in the cold. Even in the farthest dark where Pluto drifts like a thought half forgotten, gravity will keep the rhythm. The same counterclockwise lullaby that began in a collapsing cloud still plays tonight. It is the soundless turning that keeps oceans in their basins, moons in their embrace, and you right now, safe beneath its curve. There is comfort in knowing that nothing needs your attention for it to endure. The universe does not depend on our wakefulness. It holds its shape quietly, patiently through every heartbeat, every dream. As you rest, the sun will continue to breathe magnetism, the planets will trace their measured lines, and time will go on weaving symmetry out of motion. So take a moment here at the end of this long orbit of thought to feel the gratitude that fills the sky. Gratitude for the balance that never breaks, for the imperfection that keeps us in motion, for the gentle order that allows life to rest. Close your eyes. Let the solar system rock you the way it rocks its moons. You are part of that quiet machinery now, the same physics, the same pattern, the same peace. Good night, traveller of light and gravity. Good night, small consciousness within the grand rotation. The planets will keep their watch, the stars will hum above the dark, and as the universe turns on slow and steady, it whispers the oldest promise there is: you can rest now. Everything continues. Good night, universe. Good night.